So welcome everyone. Thank you to all who are joining us online and to everyone who is here in person for our workshop, Exploring Key Research Topics for our 5th International Polar Year. Before we get started, I just want to say a huge thank you to Carnegie for hosting us at their institution. It's been fantastic so far, and I'm excited to be here. And I also want to thank the committee for all of the work that you've done in planning this workshop over the last many months. You all have really worked to make this an incredible, fun, packed few days here. And then I also just want to take a second to thank the staff team who has done a really good job moving this workshop forward. So we hope that you all will enjoy the next few days. Next slide, please. Great. So just a few housekeeping things here before I hand this off to our committee chair, Craig. We will be using Zoom as the primary platform for engaging today. So all presentations in plenary will happen over Zoom, and as will the virtual activities. The chat will be disabled and all participants will be muted during the plenary session. And we ask that everyone participate using Slido in order to engage in the plenary discussions. For those who haven't used Slido before, you have the option to put your comments in the chat, ask questions in the chat, and then they will be upvoted so that the moderator sitting at the front can elevate them to our presenters in the room and online. And so I believe we just put the link to the Slido in the chat. You can also get there using this QR code. And then if you need any assistance during the workshop, please reach out to Lindsay Moeller, who will help with any questions that you might have. Next slide, please. So the National Academies is a nonprofit, nonpartisan organization that provides evidence-based and objective advice on science, engineering, and health matters. The National Academies provides independent, objective advice to inform policy with scientific findings, spark progress and innovation, and confront challenging issues for the benefit of society. At the Academies, we are committed to fostering safe and inclusive environments where all participating are treated with respect and therefore can feel welcome to fully participate in any conversation. And so we look to everyone included in this meeting to partner with us to help maintain a professional and safe environment, and want to highlight that all forms of discrimination and harassment and bullying are prohibited by the Academies. Additionally, it is essential to the National Academy's mission of providing nonpartisan evidence-based advice that participants in any of our meetings or events avoid political or partisan statements or commentary and maintain a culture of mutual respect. The statements and presentations during our meetings or events are solely those of the individual participants and do not necessarily represent the view of all the participants or the National Academies. And so for any more information on all of our policies, you can find that on our public webpage. And if you see or hear anything that makes you uncomfortable over the next few days, please feel free to reach out to our Office of Human Resources, or you're welcome to come and talk to any of the Academy's staff that are here in the room, or reach out to us via email. I think with that, I will hand it off to Craig Lee, the chair of our committee, to take it away.
Great, thanks, Morgan. So welcome everybody to what is the initial IPY 5 planning discussion for the US. Thank you for coming here today and showing up online. It's great to see so many faces. Okay, next slide. Okay, so to start, let's talk about what an International Polar Year is or could be, right? This would be the 5th. There have been 4 previously. The most recent one was not so long ago, early enough that many of us still remember the buildup and the outcome of that IPY 4. The idea behind these is to gather the community, galvanize international activity, in particular to look at kind of large-scale activities that would require a larger response, right? International collaboration, the kinds of resources that are garnered by by many nations working together. Ambitious projects in polar research, both Arctic and Antarctic. It's a time when we hope when we can actually accelerate research progress. And for IPY4, I think a lot of us were hoping that we could put large-scale observing, right, climate scale observing, the collection of climate records on a more stable footing going forward. That there might be a chance to make a step change in that regard. It's also a chance to connect the poles to global observing systems and how we think about their system at large, right? And this is kind of an ongoing effort. I think there's a large acknowledgement that the poles play an outsized role in the global climate system. But it's a chance to raise that awareness both within the scientific community and with the public at large. In the IPY5, right, we have another opportunity, I think, which is to start to translate the science into actual policy and decision making, right? In the time between IPY4 and IPY5, there's been a growing awareness of the need to connect science with societal outcomes, right, to actually connect them with benefit areas. And this is a chance for us to draw those connections more clearly. And next slide, please. So the 5th International Polar Year, currently there is a concept note online which you can read. It's still fairly broad and fairly general, right? So this is the time to actually take a hand in shaping what comes next in that note, how it develops. But fundamentally, the IPYs are meant to build on each other. Okay, a little closer. Is that better? Okay, there we go. Right, it's a chance to expand on the effort since IPY4, both to build on what was done then and to build on activity that's accelerated since then. We've seen broad ecosystem changes. My focus is primarily in the Arctic, and we've seen really rapid changes in ecosystems that affect communities that are living in the Arctic, right? It's affected food security. Those are things that have impacts both locally and downstream. These are things that in the Arctic communities we've been really focusing on in terms of how we tailor the research. There have been really large advances in methods and technologies since IPY4, right? A lot of those are isolated to lower latitudes. Some of them are currently applied to higher latitudes, but it's a chance to start to bring those things forward and to bring them into more common use at the higher latitudes, both for the kind of process level scientific observing, but also for the more operational observing, right? And one of the things we're going to talk about is the need for operational systems, right? What those motivations might be and what sorts of things we might envision doing or standing up in an IPY5. And lastly, there have been a number of planning activities that are ongoing, right? There are those in the Southern Ocean, the Antarctic. There's ICARP in the Arctic, right? And these are existing activities. They've invested a lot of time and effort in trying to understand what the highest priority science might be, what directions the communities might go in. And those are things that should be leveraged as we move forward in planning IPY5. The next slide, please. So that leads us to this workshop. I'll start by relating a little bit of history as to how this came to be. The workshop planning began right around the time of the election, right? So it was a time of a lot of uncertainty, a lot of upheaval. So there's been a lot of work that's been invested in trying to understand how to shape a workshop in the current environment, how best to generate information that would inform activity going forward, and indeed what activity we might expect to be able to advocate for. So we appreciate everybody's understanding in this. We know that invitations went out very late, very, very late for some of you. And we really appreciate people's ability to respond very quickly to those invitations. We know that the announcement for the workshop came out fairly late, and we were overwhelmed by the response, both virtual and for in-person participation. So this is great, right? We have a healthy community. We have one that's interested in engaging in conversations about what comes next, right? We're planning for something that's 7 or 8 years down the line. So it's quite a ways out. The motivation for that planning was that for IPY4, there was this feeling that we launched into it without actually having had enough time to advocate and generate resources right, to plan for the level of activity that we might have liked. And so for the fifth IPY, the hope was that if we began this planning long in advance, had these discussions, we might be able to advocate for a higher level of resource, right? But we might at least be able to organize ourselves to make those arguments. So where are we at with this workshop? The key goal here over the next couple of days is going to be to try to identify both big scientific questions and big operational needs that we might focus on for an IPY5. And the way this will work is that the workshop report that comes out of this will include whatever we've talked about, right? It can't include things that weren't discussed in the workshop, but if there are ideas about what we want to do, about the science questions we would like to pursue, about systems we'd like to build, about infrastructure that's needed to support that science or support those operational needs, we need to articulate them here over the next couple of days so they get into the report. And the better job we do with that, the more coherent it is, right, the better their arguments will be. This is the first conversation of what will hopefully be many, but that material will propagate forward. So if we can build a good foundation, I think it will put the next conversations on a good footing. We're hoping to concentrate on ambitious goals, right? Things that require an IPY level of activity. Think about things that require lots of collaboration, that require intensive resources that might be hard to argue for in an individual science project. Things that you might envision could be sustained long past the IPY, right? That might get their start in an IPY, the buildup of a system or the start of a question. We want to draw the connections with societal needs, so ideally we can actually trace back and point to benefit areas that what we're doing would contribute to. And then the last note, right, if you look at the agenda, there are a number of examples that are included, right? We kind of organized it around a few science themes. Those aren't meant to be the only science themes, right? They're meant to be examples to start the conversation. So please feel free. We're hoping that people will throw out other ideas and other themes over the course of the meeting. Don't feel constrained by the themes that are on the agenda, right? We're trying to get a much broader set of inputs. The hope is we'll highlight advances in approaches and technologies, right? I said before, there have been these large advances in what we can do. We should be thinking about how we might apply those advances in these settings, right? Whether it's the start of trying something new or whether it's scaling up something like profiling floats, right, into a broad region where they don't currently operate. Partnerships and collaborations will be important. We'll talk about that a lot in day 2, right? But an activity like this is not a one or two researcher activity, right? The idea is to build large groups, large collaborations to tackle big problems. And then lastly, part of the focus of this was to actually actively recruit early career researchers, right? These are the people, some of you are in the room, who will be leaders by the time IPY5 comes along. So the hope is to draw you into this conversation early and to find ways to put you into leadership roles, right? Either partnering with senior people or helping out in various places so that you're in position by the time that fifth IPY comes along. Next slide, please. So this is the workshop planning committee. Most of us are here for the workshop. I think Kana unfortunately couldn't join us, but the rest are here or will be here through the meeting. So you can find us and chat with us throughout the meeting. Happy to talk about the process or ideas or anything that comes up really. Next slide, please. So a quick run through the agenda. There are a number of pre-recorded webinars online, and that number should be growing over the course of the next couple of days. Again, some of these were recruited fairly late in the game. This was an idea that we owe to Jenny Baseman, who's sitting over there on the, or in the back somewhere. Anyway, the idea that Jenny had was that it would be great to to set up a bunch of small webinars talking about what the polls might look like in 2030, right, as a stage setting for our conversation about an IP Wi-Fi. So you can see from the list here, we've got webinars covering a number of different topics. Whoops, my screen just went blank. There we go, got it back. Please go online, take a look at them. People put a fair bit of effort into doing that, and the hope is they will be a long-term record that we can refer to as we move forward. Next slide, please. So we are here, day one. After the introduction, we'll have a session that Andrew will lead or facilitate, which is Polar Science for Society. And this is meant to set the stage, right, to talk about the role that science and the poles plays in society, how the poles impact our society. There'll be a panel. The original idea for the panel was to bring in people from a number of different stakeholder and rights holder areas, right? Not just science, but think shipping, right? Insurance companies, what have you. Due to timing, we're not quite there, but we have some people who can speak to those applications. And it should be a fairly interesting session. Session 2 and 3 really get at the heart of the matter, and these will be critical for how we move forward with the meeting. Session 2 is meant to start to draw out scientific questions and operational concerns or needs that might be addressed by an IP Wi-Fi. So there'll be a number of panelists. They'll talk about things that they envision as being fertile areas for work in IP Wi-Fi, areas of need. There'll be an interactive activity in which we'll try to draw out from both the virtual participants and the participants here in the room input for those discussions. And that's really the opportunity to put forward ideas, right? It's the opportunity to talk about what you see as being the really key science questions or the key observing system needs, right? That you envision we could go after in IP Wi-Fi. That'll motivate session 3, which will talk about capabilities and supporting activities. So think technologies, lead agency agreements, international agreements that facilitate shipping across boundaries, right? New methodologies for getting at certain measurements, right? That this is the whole list of things that affect how we do our science, how we collect observations, how we run models, but really tied to what comes out of session 2, right? So from what we've heard in session 2, what capabilities can you imagine that we really need? Things that we might develop, things that already exist, things that need to be deployed in a broader fashion. The next slide, please. So day 2, after recapping day 1, we'll really focus on human capacity, how we do our work, the people that are involved, the complexity involved in different field activities or different programs, and how we go about supporting the people that are needed to do these things and supporting how they interact. As I said, the takeaways from this are a report that our colleagues from the Academy will write. The report will include whatever we've talked about here. So it's really important to get things out in the conversations. The target for that report, other than our sponsoring agencies of NSF and NASA, would be anybody within the funding environment who's interested in listening, or members of our community, right? As I said, this is meant to be the start of a conversation, not the end of it. So it's the opening set of remarks, if you will, about how we might plan for an IP Wi-Fi. And with that, I think we're transitioning to next session, right? So Andrew Lloyd is going to chair the next session. Andrew is a geophysicist from Lamont Doherty, and this is our scene setting session.
Hi, everyone. Welcome. Can you all hear me in the back? Great. Excellent. I'd like to welcome you this morning to our first session, Polar Science for Society. In this session, we're going to focus on how the Arctic environment change impacts the lives of northern residents and how those changes at both poles affect the lives of those living at the lower latitudes. Polar research provides understanding and data products to inform decisions across a wide range of sectors, including human health, zoning and property insurance in coastal regions, predictions of communication disruptions, and the understanding of how ecosystem shifts impact both commercial and subsistence hunting and fishing, among many other things. So as you hear our talks this morning, I'd like to invite you to think about how your science contributes to society, and think about those ideas and then relay them to us either in Slido or during our panel discussions. To start off, we're going to begin with a keynote that's given by Dr. Richard Alley. Richard is the Evan Pugh University Professor of Geoscience at Penn State. Richard has studied the great ice sheets to help predict future changes in climate and sea level. Richard's a member of the National Academy of Sciences. He's a foreign member of the Royal Society, and he participated in the UN International Panel on Climate Change, which received the 2007 Nobel Peace Prize. Many of this room likely know Richard for his entertaining and engaging lectures and his passion for teaching. I myself, as a former student of his, got to enjoy that. And I'm very pleased now to hand this over to Richard to kick off with our keynote talk. Thank you.
Hey, Andrew, thank you. Great to see you. And I'm so sorry I am not there. It is, I would love to be there. But at any rate, I hope we're headed towards. So if it is a problem, if you cannot see my screen, please yell. And if not, I'll presume you do, and we're going to roll ahead. We'll get a pointer up here so I can scribble on things, and we will see what we can do. It is fantastic to see so many of you, and I can't see all of you in the room, but those of you online, wow, what a group of people. So at any rate, let's see what we can do. Big thanks to the National Academies and Morgan and Annie. They are doing a very hard job in a very difficult environment right now, and just a huge hat tip. Thanks to Carnegie for hosting you there. The IPY committee is ahead of things, and this is important, right? My mentors, almost all of them actually, were part of the third IPY, the IGY, and we're only two people removed from that, which is sort of amazing. So you had a very nice introduction there to where this is going, which ended with the call for people. I want to turn that around first and start with the call for people, for education and outreach. I have a dad joke on here because I'm a dad. So we are going to turn this around and inspiring people, letting our young people know that there's a future in this field is the most important thing we can do now. And this is really a big deal. This is this is true. This is the refrigerator freezer of people who have a granddaughter now. But these are people who used to have two daughters who were young, and now one of them is a brilliant science teacher and one of them is a brilliant glaciology professor. And their art used to be on this freezer. And if you peer closely on this freezer, most of you probably remember this meme from more than a decade ago. The penguin talking to the polar researchers. Yes, I would like to science, please. This just ran everywhere. The polar researchers are inspiring. You make a difference. You really do. These are a few of our current students, and one who just graduated and has a wonderful job, who are sciencing. This is the people who are going to science in the future as we roll along. I worked with a student many years ago, Air Force ROTC, went to Greenland with us and was studying ice cores, and mostly for C-axis fabrics, but was measuring the sound velocity in the core. And if there's a little crack in the core, the sound goes slower. and then was commissioned as an Air Force officer and was put in charge of a project to make sure that the planes are safe. You can't see the crack in the airframe under the skin, but if there's a crack, sound goes slower. And the student had learned in polar research how to do this and was then guaranteeing the safety of our fighter jets. Another student more recently went to Antarctica with Sridhar, was working on the stability of thwaites using geophysical techniques, then went to work with a commercial company generating clean water systems for people, and then was put in a big position. Where and when is there danger to the crews rebuilding Los Angeles from slope stability issues? So you've got polar research that turns into national security. It turns into recovery from disasters. It is unequivocal that IPYs excite students. What you do there is important, and you're going to excite the students. You're going to excite the public. We've got to get people into the field. Yes, we need remote sensing. Yes, we need models. Yes, we need lab work, but we've got to have people in the field and they have to tell their stories coming back. Okay, so yes, I would like the science, please. All right. So that's important there, and I'm not sure where my pointer went, but I'll try to get my pointer back here. And so next, what I'm going to do is do a few topics on things that possibly I know something about and possibly that are worth highlighting. And I'm going to start with the one that our group mostly works on now, which is sea level rise. So this is news. I copied this in fair use from good people who were reporting things. This is 2023, and in 2023, the Army Corps of Engineers was fairly close to getting $57 billion to build an Ike Dike. Protect Houston. We don't know if this will ultimately be built or not, but the Corps of Engineers can provide good documentation that this investment is justified, and we have a cat. That this investment, 57 billion for one city. You can find online the 52 billion for the Sandy Shield for New York City. You can find San Francisco Bay at 110 billion, another 13 billion for the port. That's 232 billion for 3 U.S. cities. Okay. 3 U.S. cities. That's a very small part of the coast of the US, which is a very small part of the coast of the world, and we're up to $232 billion. All right. Now they look at sea level rise. There's a high, there's a medium, there's a low. They pick one of those. What if they get the wrong one? What if we have misled them on how much sea level rise there will be? Okay, so they may be building too high a wall. And what are they doing? They're wasting a lot of that 232 billion plus all the other investments for all the other cities that they're going to work on. We're going to lose ecosystem services. We're going to lose recreational opportunities. We're wasting a lot of that money if they're building too high. But what if they're building too low and they don't respond really rapidly in case that they realize that? They're, of course, wasting the construction cost. They're going to lose a lot of valuable things that they have promised to protect. But there's also a lot of people who are going to settle behind those walls once they're assured it's safe. They're going to put their lives and their property there, and you're going to lose all of that too. And we know what that looks like. This is what it looks like. Hurricane Katrina, in total, the damages were $300 for each person in the entire United States. And it was lives, and it was art, and it's a horrible, horrible thing to think about. And New Orleans was not that big a city, right? It really wasn't. So we've got to get this right. The investment is immense, and the potential for wasting it is immense. Now, this is the most recent IPCC guidance going to inform the Corps. Under low warming, they're expecting sort of 0.5 meter of rise. Under high warming, up close to 1 meter, unless something goes wrong. And we'll come back to that. Okay. I can show you the papers. Garner et al. Showed that the IPCC is typically giving central estimates that are lower than much of what's in the supporting documentation. Andra studied at Penn State. You can also see the earlier IPCCs have had central estimates of rise which are lower than what then occurred. Stefan Rahmstorf especially has worked on this. So there's no evidence in any of this that the IPCC is overhyping it. There's evidence they may be too low. And a lot of that may be because they're relying on models that have not included a lot of the processes that could cause faster sea level rise. These processes are poorly documented, they're poorly parameterized. We don't know how to put them in the models, but the processes of things like water sneaking under the edge of the ice sheet where it's nominally grounded and melting it farther inland have been set to zero. The ice shelf loss often does not occur in these models. The ice is undamaged, but anyone who's looked at the front of the ice knows it's hugely damaged and that fails faster. There's a whole bunch of processes that we can't parameterize well that have been set to zero in the models. Okay. Now, in this higher one here, this one right here, by 2100, Greenland loses 2% of its sea level equivalent. Antarctica loses 0.2% of its sea level equivalent. It is very, very hard to make a future which is actually better than these when you're only losing 0.2% of what Antarctica can do to the sea level. It is very easy to make it worse. And that's sort of what these are up here. And be very, very clear. This is not a worst case scenario. That is not a limiting scenario. Okay. This is a fantastic piece of work by people who are overworked and underpaid. They are fantastic modelers. They are doing brilliant things. They got together and usually without enough funding, and they said, what do we get? This is just Antarctica. What do we get as we warm into the future under strong warming? And this is the key result for me, at least. Remember again that these models tend to be lacking some of the processes that could make it go faster. So this is not worst case anywhere. But running it out in strong warming into the future, this is the range of sea level changes that came out of the models from growing Antarctica and lowering sea level by 0.5 meter to shrinking Antarctica and raising sea level by 7 meters. And you can notice that they're not hugely clustered. These are not gross outliers in what you have. And so what this paper says is they highlight, first of all, that Antarctica can raise sea level. And secondly, the choice of ice sheet model remains the leading source of uncertainty. The choice of model is the leading source of uncertainty. If you've ever seen an endorsement for an IPY to help them do better, this is it. And we need better data. And this will be field, it will be remotely sensed. We're going to have to do things in the lab. We're going to have to build simple models using theory. This is going to have to lead to parameterizations that they can use so that they can build improved models that assimilate data. And this is going to take serious support. But be very clear. If the Corps of Engineers said, we want to spend 1% of the cost of defending just 3 U.S. cities on an IPY to get it right, that would be $2.3 billion. If somebody gave you $2.3 billion, you would be crushed under the flood of money. You'd have no idea what to do with it. So be ambitious. The value of what you are talking about here is so immense because 230 billion for 3 cities is just the tip of a big iceberg here. Okay. Now, The ice sheets are losing mass. That is going into the ocean. That makes a difference. This paper was from Gavin Schmidt and a whole group of really good people very recently. And they said, the models are not doing as well as they should on atmosphere ocean evolution. Why? Because they're not including the mass fluxes from the ice sheet that have been increasing as the ice sheets change. All right. 50 years ago, communities had to make decisions. How do we start to build these models? And they generally assumed that the ice sheets are big white mountains that are not interactive parts of the Earth system. They're just big white mountains that don't change. Okay, they're the world's most boring ski areas. And that's been built into the models for a very long time. It has to be fixed now because the changes in the ice sheets are changing the ocean atmosphere system. They're affecting our predictions, they're affecting our reconstructions. It's not easy. If you built an ocean that interacts with the atmosphere across a free surface, how do you jam it under an ice shelf where a whole lot of the water mass conversion is actually happening? But if we're going to have good projections of the future, we're going to have to fix this. Okay, this is a big task. Here's one. In the modern world around Antarctica, the warm waters mix up offshore and they bring up CO2 and they bring up nutrients that lead to all sorts of fisheries and productivity. They affect the sea ice down there. There's a huge amount of really, 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 really important stuff going on in the Southern Ocean. If we put too much meltwater in, this goes all the way back to Suki Manabe. You put too much fresh water on the surface, you're going to change. It cools. You might grow more sea ice. You're going to change nutrient availability. You're going to change fisheries. You're going to change almost anything you can think of. And you're going to roll the isopycnicals over and hose that hot water right at the most vulnerable part of the Antarctic ice sheet and drive sea level rise faster. And this actually happened during the previous ice age at the other pole, and we had these giant outbursts of icebergs known as Heinrich events. We could trigger really big things. And right now, this is not changing in most of the models. Okay. Now, the other end, right? Greenland is losing mass too. We're seeing an intensification of the hydrologic cycle. It is changing freshness in the surface ocean. And that leads to very interesting questions. And no, this is not going to happen. We know that. But the last time nature put a huge amount of fresh water in the North Atlantic, this did happen. And I've got some dries in here in places that a couple billion people now live. And, the public and the policymakers don't know what to think. Is this a complete nothing burger? We can ignore it. Is there something here? Is it a big deal? What is going on in the North Atlantic and what will it mean? And they're confused. A lot of us are confused. This is not just a polar problem. This is a much broader one, but it is a polar problem. And we really do owe it to the community. We owe it to the public and the policymakers to get rid of a lot of this confusion. What are the freshwater fluxes? What is it going to do to coupled ocean atmosphere circulation? We can't pound on the table about this at this point. Now, I worked on this way back. I made plots like this one, and this is recent over here. This is the medieval little ice age that actually affected the way people lived, and this is interesting. And this right here in Greenland was 10 Celsius in a few years. And what was it? It was mostly changes in sea ice in the winter. It was the difference between having sea ice in the Gensees and not having sea ice in the Gensees, and a few other places. Sea ice matters, especially in the winter, but also in the summer. And sea ice, as we all know, is shrinking. This is a big deal. And you all know this, but I'm not sure everyone does. As the sea ice shrinks, it increases the need to understand sea ice. It increases the need to break sea ice. And so here's a couple pictures that I swiped from out on the web. And you might possibly remember this one. This is the Canadian Coast Guard ship Amundsen breaking ice in the St. Lawrence to rescue some ferries that were trapped. And this is the St. Lawrence in the summer. Okay. It is still not too hot to need icebreakers in the St. Lawrence. A lot of warming before you get rid of the need for ships. And the truth is, when the Arctic Ocean was impassable, ships didn't pass. You don't have to go rescue anybody. And now the seasonally open water is luring shipping and tourism and fisheries. And yeah, we can make one more dash across before it freezes. Oh, we didn't make it.
Richard,
The need for ice breaking
one-
is going up. The need for forecasts. What's this afternoon? What's tomorrow? What's next week? What's next month? Seasonal. What will the year be? Should we be planning for next summer going across the Arctic, or should we be going around? And long term, how many icebreakers? How many ships to go up there? The more we do up there, the more we're going to need ice breaking. And as the ice shrinks, the need for ice breaking goes up. The need for sea ice projections goes up. We've got to understand this. Okay. Now, when I go out and talk to the public about this, I do ice sheets and I do sea level and I do ocean circulation, and they say, but what about the polar bears? Okay. Guaranteed. And so this is a fascinating paper. Alex is a brilliant scientist who's actually married to our daughter, the glaciologist, Karen. At any rate, this one, if you didn't read it, I would recommend it to you. But at the bottom, it says extirpation for polar bears in this region may already be inevitable. And after this came out, first of all, I'm letting this stand in for an immense number of questions that I don't know much about, but that I think are really, really important. And biodiversity and traditional lifestyles and fisheries, and there's just this huge range of things that are almost certainly more important than the stuff I'm focusing on, but that largely fall outside my limited expertise. But you have people there who will expand on these. So be very, very clear on the importance of these things. When this came out, the family, actually, we went up to Churchill. We all wanted teaching slugs. We wanted to understand what was going on. I've got to tell you, Churchill is a fantastic visit. They are wonderful people. It is a beautiful place. The bear watching was unbelievable, just unbelievable. But that's because the climate stinks for the bears. And they're stuck on land and they want to get out on the sea ice and catch seals and get something to eat. And they were standing there starving to death because they couldn't get on the ice. All right. It's so enjoyable and so hard to enjoy. It's hard. Now, I walked into a senator's office once after the IPCC round, and the senator looked at me and said, "Oh, climate has always changed naturally, so we should not worry about humans changing climate." Right? Can you imagine walking into a senator's office and having the senator say, "Oh, fires have always burned naturally, so we should not worry about humans causing fires"? Right? There's no arson, there's no accidents. Can you imagine a senator saying people have always died naturally, so we should not worry about humans killing each other? Wars and murder and what? Can you imagine? Climate has always changed naturally, so we should not worry about humans changing climate? Climate has always changed naturally. That proves that climate is changeable. Climate change has always affected living things. That proves it's important. And climate has changed for many reasons, but be honest, CO2 is the biggest control knob on the history of climate. And in my experience, the more we learn about past climate change, the more worried we become about the future. We could cause bigger and faster changes than almost everything except the meteorite that killed the dinosaurs. And if our understanding is wrong, the history says climate change is more and it affects life more than our models say. And so we have a big imperative to understand the history of climate and not just ice cores. This is around the
Richard, if we
glaciers. This
could
is
wrap it up shortly, that would
very,
be
very,
great.
very soon.
Thank you.
Very soon. This is the history of permafrost. This is the history of the ice sheets. This is why do our models seem to lowball it? Okay. The last time nature emitted a huge amount of carbon, the land surface started emitting more. Is that going to be fires in the boreal? Is that going to be permafrost smoldering for decades? We need to do that. Last piece, and then I'll shut up. This is a paper. You could read the text sometime if you want to. There is a very persistent narrative that the warming hurts almost all the people of the world, but at least it helps the finances in the Arctic. And you can find lots of publications like this. But when I've talked to economists, they say, I'm not sure we really included how long the changes will last and how disruptive they'll be and the value of the things we're losing and and what happens if your neighbor goes down the tubes. Do you get stuck in a trade war or something? And can you really count on good things when all your neighbors are going downhill? Can we get an IPY that actually thinks about the real economics of the Arctic? Right? And I haven't said anything about politics and about wargaming over Svalbard and about the value of the Antarctic Treaty. But 230 billion to protect 3 US cities, the value of information from an IPY grossly exceeds the cost. Okay, on so many issues. So yes, I would like to see science, please. Thank you.
Thank you, Richard, for that excellent talk, tying our science that we do in the polls to society and how it impacts society. We're running a little bit behind right now, so we're going to take a few questions from the audience and a few questions from online, and then we'll move on to our next session. So those in the audience, think of a question, and we're going to start with one online first. So this is from Dr. Alessia. Given Richard's excellent talk, what if we do science that accommodates the uncertainty? In other words, build a range of potential futures, low, medium, high estimates using modular instead of old fixed sunk costs. Do we have any, Richard, do you have any thoughts on that? Or anyone in the
Yeah,
audience?
brilliant. I think that there's two imperatives. One is to build for the range of possibilities, and the other one is to try to narrow that range. And I think both have to follow. So much of this sea level rise stuff goes into things breaking, and many other parts of this involve things breaking. And I have a minor in metallurgical engineering, and I took the broken things course. And the professor, if you drop this, it might break in two and it might smash into smithereens. And I can give you a beautiful probability density function of how things break, but I can't tell you how the next one will break. And the engineering professors say, never get yourself in the position where you have to predict a fracture accurately because you'll fail. And so making the ice sheet models just right when we're worried about things breaking off is always going to be difficult. So you've hit a very, very important point.
Thank you. We can go ahead and take a question from the audience. I just want to remind everyone, if you could please log into Slido and put your questions there as well. It'll help us preserve those questions and also get them upvoted so we can discuss them. Do you have any questions from the audience? Okay, we have another one here in Slido. This is from Ginny Cantina. Sorry if I'm mispronouncing your
Tanya,
last
hi,
name.
Jenny.
Richard, thank you for your perspective. I agree that we must educate, but how do we financially support students in the current administration?
I
Sorry,
hope
folks.
I hope we have that discussion. We're having it at home. We're having it here. If we've got to work with our with our universities, we have to work with TAing and what have you. I think when we can talk to philanthropy, the most important issue for us now is going to be keeping this generation of young people alive. If you can talk to a philanthropist, if you can talk to your dean, if you can talk to your president, if you can talk to anyone, we've got to keep this generation. Take my money away. I don't have any, but take it away. Just, I don't need anything. We've got to keep this generation of young people alive. And that has to be the highest priority because right now they're looking into an abyss and they're scared. And new offers are not being made, whether we can support the old ones. This just has to bubble up to the top. And because if we lose a generation, Jenny, I mean, come on, you're a hero of these things. So yeah.
Thank you, Richard. And we'll just one more question real quick, and then we'll move on to our next session. In your perspective, how can we, oh, sorry. It keeps moving on me. Oh, okay. How can we best celebrate our triumphs and be crystal clear that science is not where we need to be in order to prepare for the future? The public may see our paper and think things are solved.
Yeah. I mean, so many of you, and I scrolled through the names that are on there, and so many of you have been doing this and have been doing it well. But I think we need to redouble our efforts to get. I spend a lot of time giving public talks now, and I usually start here. Right? This is a little bit of sand, a little bit of oil in the right rocks, and science and engineering. You've got Einstein in your pocket, right? The GPS uses both special and general relativity, and the error is such that if we didn't have Einstein, the nice lady in the phone would get lost in 2 minutes, right? And then usually I tell stories on me. So you don't need this, and I apologize, but I have a fake aorta. Okay, I inherited a problem that was going to kill me. And I went to the Cleveland Clinic and they took me offline and they gave me 4 inches of knitted, not woven Dacron. And they woke me back up and said, "You're fixed. Go on and live your life." That's science. And we have cell phones and we have jobs and we have saved my life because of science. And we know beyond any shadow of a doubt that meteorology makes weather forecasts that are grossly more valuable than the cost of getting them. And the advice that IPY is going to give people is grossly more valuable than the cost of it. And so we just all have to be telling that story. And it has to be a diverse suite of us all. Because right now, there are so many pieces of the US that choose who to listen to. There are people, I'm sorry, I'm not sure who asked this one, but if it was Jenny, there are people who will not listen to me, but they'll listen to Jenny. There are people who will not listen to Jenny, but they'll listen to me. This is wrong, but this is the reality. We need all of us because we need a diversity of communicators who are telling the story. And so that's it, it's just we're doing it, but we got to do it more. We got to do it better. And I think we have to start at the things that really resonate people, like their ability to have a cell phone and their ability to save their life if they get sick. And then we can get to the ones that our work, which is cost effective. And so I think we can do this, but it's not going to be easy.
Thank you, Richard. We're going to go ahead and transition to our panel. But thank you, Richard, for the excellent talk and the answers to the questions. And we hope you can stick around and participate as well. So we're now going to move on to panel 1, applications of polar science. And in this session, we're going to focus on actionable science. So how polar focus research and the resulting data and understanding informs decision-making and impacts everyday lives. We'll be hearing from speakers who bring perspectives on a wide range of topics that touch on how polar science connects society. During the session, we'll have 3 different speakers. 2 will be virtual, 1 will be here in person. and they will inform us of their science and how that informs decision-making and impacts our daily lives. After each speaker, we'll have a very brief window for clarifying questions, although we're a little bit behind, so we might not do that. But please put your questions requiring longer answers in Slido so that we can discuss them afterwards. Our first speaker is Robert McCoy from the University of Alaska Fairbanks. Dr. Robert McCoy is the director of the Geophysical Institute in Fairbanks, Alaska. He's a scientist scientist at the Geophysical Institute, study a broad range of geophysical and space phenomena, some of which Robert is going to discuss with us today. Prior to this, Robert served jointly as the program manager for space science and technology programs at the Office of Naval Research in Arlington, Virginia, and as the technical director for the Operationally Responsive Space Office in Albuquerque, New Mexico. So not only does Robert bring a lot of insight into the workings of the Geophysical Institute in Alaska, but also how things and what things are needed for our military. Thank you, Robert, for joining us from Alaska, and I'll pass it over to you for your talk.
Yeah, thanks, everybody. And sorry I couldn't be there. I tried. I made it as far as Seattle, waited 6 hours. The plane broke, and so I just said heck with it and came on home. So today, in my short talk, I'd like to talk about who we are and what we do in the Geophysical Institute and what we see as opportunities and challenges in time of IPY. My colleague, Elisa Alexander, she's going to talk more about how climate change affects people living in the Arctic. So I'm going to let her concentrate on that. We say that we're strongly shaped by where we live up here in Alaska. We're at the crossroads of the intersection at the Ring of Fire and the Aurora Level. Next slide. So the Geophysical Institute was created in 1946 at the end of World War II by Congress, mainly because of the aurora and effects on communication. But there's a wide variety of phenomena that we study up here in Alaska and also around the circumpolar Arctic. Next click is the aurora and space weather. That's why we were created, and one of the things that we focus on. In the winter we see space weather pretty often. Next click. We have 54 active volcanoes in Alaska. There's about 3 erupting all the time. There's one about to go somewhere at Mount Spur near Anchorage. People are a little nervous. Next click. 90% of the state is permafrost. I'm going to talk about permafrost a little bit more. 50% of the Arctic is permafrost, and it's a big deal up here, especially with the changing climate. Next click. We have an earthquake every 10 minutes in Alaska. It's very seismically active. Next click. We have 1 million square miles of sea ice. Our faculty go out and help the Navy with ice camps, ICEX and SIDEX, but a lot of sea ice is changing. The changing sea ice is actually changing a lot. We just heard about, Richard talked about the effect on polar bears, but sea ice is changing for the people in the Arctic. It's been an enabler, and now it's a problem as the sea ice retreats. Next click. 30,000 glaciers. The glaciers are melting. Actually, as the glaciers melt, we're getting more coastline here in Alaska. Next click. We have very, very extreme weather. We get strong inversions. We have sometimes the worst air quality in Alaska here in Fairbanks. And finally, the last click. We have more coastline than the rest of the lower 48. The sea ice is retreating. You just heard there's more fetch, higher wind action. The permafrost is thawing and subsiding. It's a real problem, and it's all accelerating. Next slide. Next, I'm sorry, go back one click. Yeah, the last click is everybody knows the Arctic is warming 3 or 4 times as faster than the rest of the planet. Next click. So we're very operational in the Geophysical Institute. We monitor those volcanoes and earthquakes. This is a great place to downlink polar orbiting satellite data, and in particular, synthetic aperture radar data. We have 12 satellite dishes. We pull down 40% of NASA's polar orbiting data. We pull down a lot of data for National Geospatial Intelligence Agency, and we measure around the Arctic SAR, climate change. We measure, we have change detection and changes in landmass. We have a rocket range. We launch rockets into the Aurora with NASA. We have a very large drone program, and drones have will have a lot of impact in the future. We pull down NOAA's weather data, snow, ice, and clouds from the Joint Polar Satellites, and the GI is a UARC, DoD University Affiliated Research Center. We have a network of seismic and infrasound sensors. We listen for loud sounds like nuclear explosions or also volcanoes and meteors. And finally, we operate HARP, and we have a lot of good ideas how to use HARP for the future. Next slide. So our UARC has a global network of infrasound and seismic sensors. Like I said, we have some at the South Pole, some at McMurdo. We're listening for loud sounds, but we also hear a lot of other geophysical interesting phenomena. Next click. Permafrost. I put this slide up to talk about one of the things we're supposed to talk about is international collaboration. We used to collaborate strongly with the Russians across Kamchatka and Siberia, but since Ukraine war, that stopped. But these holes are opening up across Siberia. The permafrost thawing, releasing methane, and something's exploding. Truck-sized chunks of dirt are blowing out, and this seems to be accelerating. This. Hopefully by IPY, the war will be over and we'll be back collaborating again. Next click. We have a large network of seismic and infrasound stations around Alaska. Some of these we've been able to add space weather sensors and weather sensors. Weather forecasts in Alaska are terrible, but this is a way to potentially increase the weather forecast by including this ground-based data, which has never been in the models before. Next slide. I mentioned we have 2 rocket ranges, one in Kodiak that launches to the south. We launch from just north of Fairbanks, suborbital to do science. Next click, we're working with NASA and the Department of Defense to have other launch opportunities in Alaska to perhaps reach the cusp of the magnetosphere for improved space weather measurements. Next click. I mentioned HARP. HARP was built about 25 years ago. We've been using some experiments lately. We're doing experiments to look at HARP as an over-the-horizon radar. A lot of military applications, but also to measure sea state, sea ice. We think we can reach out from the middle of Alaska out 4,000 kilometers in any direction in a complete circle. Next click. So this is my last slide. Could you click again? This is what we see as opportunities in the IP-wide timeframe. We see the need for lots more data, all types of data, especially high resolution and artificial intelligence to make sense of all this. We need more radar and optical data. A good example is the NASA NISAR mission, which is about to launch. There'll be 3 to 5 meter resolution L and S-band SAR. It'll be generating 50 petabytes a year. This is just one example. We need a lot more of that. We see some real opportunities for drones, for Arctic observations, but also in Alaska, drones are important, will be important for cargo delivery and emergency response. And finally, and Lisa will talk more about this, we need to combine local observations, incorporate indigenous knowledge for co-production of science. Next click. So we're all worried about what's the emphasis in climate change research, but there's an increasing focus on Arctic security. And this dual use, this is an opportunity. Sea ice will be important for Arctic security to monitor shipping lanes. So the DoD will want to know more about how to monitor and measure the sea ice. Some of the data sources will provide improved weather forecasts. Wildfires, and Elisa will talk more about this, are still important. And also, as I just mentioned, we'll have more access to space and we need improved space weather forecast. And this is my last click. So other potential science enablers for Alaska, a lot of interest in critical minerals and also geological hydrogen. These could be real enablers to find more science enablers, more development. And for example, for the critical minerals, there's interest in moving micronuclear reactors to Alaska, maybe put them near mines to smelt ore. So these are what I see as the challenges and the opportunities.
Thank you, Bob. I think in the interest of time, we're going to go ahead and introduce the next speaker, but there will be ample time for questions during our panel discussion. Our next speaker is in person. She is Dr. Elisa Alexander from the University of Alaska Fairbanks. Elisa is the director of the Center of One Health Research at the University of Alaska. She has extensive expertise in tribal health, experience, in tribal health to the College of Indigenous Studies. And her research spans the intersection of public health, environmental health, and animal health, emphasizing food security and sovereignty, climate change, human health, and collaborations with Indigenous communities. Thank you, Elisa, for joining us. And when your talk is over, you're welcome to join us at the panel table.
Okay, hello. Can you guys hear me? Great. Masit Cho for having me. I appreciate the invitation and I feel really honored to be here. I come here as a clinician mostly, so I'm a new scientist. I joined the University of Alaska Fairbanks in 2023. So when I was looking at preparing this talk, I kind of wanted to share with you some of the issues that we're seeing in the north that we're concerned about, and kind of opportunities for gaps in knowledge that we have currently. So next slide. Bangwinzi, Shojri, Elisa Alexandroji, Vantakwichin, Ihlika, Tanangwichi. So I come from a community called Old Crow, which is in the northern Yukon Territory. About 5 years ago, my community declared a climate change emergency. We are very isolated in a small community. I currently live in Fairbanks and I work at the University of Alaska Fairbanks, as mentioned, with the Center for One Health Research. Next slide. I wanted to provide this slide. I'm sure a lot of you that have worked in the north know this information, but it reflects the indigenous languages across the north and the circumpolar north and the family linkages in those communities and in those languages. And so we are not defined, as you all know, by borders, political borders. Our communities have relationships across countries. And so one thing I really wanted to emphasize as well, and for many of you that have worked in the north, you may already understand this. When we think of the north and we think of communities in the north, a lot of times I think there's an assumption that people live in those villages or those small communities only. We travel all over our territories and land. And so this map, to me as a physician, looks like kind of veins. On the far corner is done by the Dene Nation in Northern Canada, and they mapped all of their trapping and travel trails in their country. And so it's really important for scientists to understand that your science and your practice is not separate from the people, and it still impacts what people are doing as they move through their land. We don't stay in one spot, and most of us in the north come from nomadic people. Next slide. Part of the reason I think I was invited was my experience in tribal health. So I'm trained as a physician in Canada, but I've spent 12 years working in tribal health in Alaska, and I still work a little bit with the Community Health Aid Program with Tanana Chiefs Conference. So tribal health in Alaska, tribes have compacted their healthcare and they deliver healthcare on their own. 90% of the healthcare in Alaska is delivered by tribal health. So if you live in a village, whether you're indigenous or not, your healthcare is delivered by the local tribal health organization. What that means when you look at healthcare in the north, from a geographic perspective, that FAR map there demonstrates what our road network is in the north. We don't have a lot of roads. Most of our communities are fly-in only. I think the statistic is 80% of our communities are off the road system. So the far top corner one looks at the flight patterns for referrals for emergencies, medevacs, medical care. A lot of communities will have local small clinics that have healthcare delivered by a locally trained community health aide, and only the larger hubs will have physicians, physician assistants, nurse practitioners. The geographic area that we cover is highlighted in the green, red, and blue map. So the red is the size of the state of Alaska. And the blue area was the area that I worked in when I worked with Tanana Chiefs Conference. I think what that means from a science perspective, one, as Bob mentioned, the opportunities for technology to deliver improved healthcare and stable healthcare to those villages. So looking at drone technology to deliver healthcare in emergencies, when there's weather events that planes can't fly in for, delivery of medications, more cost-effective ways to do that. But also as scientists, you're going to be going into these areas. And when you go into these areas, it doesn't mean that you're not going to have medical issues or concerns. I've medevaced people out with appendicitis that came on suddenly. So these are all considerations. Next slide. So the Center of One Health Research, some of you may know this, One Health looks at the intersections of human, animal, and environmental health. This is the Venn diagram that was developed through UAF and looks at the departments at UAF and how they intersect. And so for the rest of the points I'm going to raise, I'm kind of going to use the One Health lens. Next slide. So zoonotic disease, 5 million birds from all over the world come to the north to have their young in the springtime. And what does that mean? It means that they're feeding and, consuming the plants and bugs and everything in your areas, and then they're coming to the north and bringing that with them, and vice versa. So when we have things like permafrost thaw and mercury thawing from that permafrost, when we have things like avian influenza, those things are being transmitted by these wildlife that are traveling through the entire world, really. One thing that I did not include that I did want to bring up is the salmon collapse that's happening in Alaska right now in the north. In the region that my husband's from, we are a fishing community, and for the last 8 years, we've been banned from fishing because there's not enough salmon to get into the Canadian regions. And how is that impacting the global ecosystem? Those salmon are food in the ocean, and they consume food in the ocean, and they're a major part of the, 1 minute. Okay, next slide. Okay, I'll be really fast. Bob touched on this. So permafrost thaw and Yedema, very sensitive types of and special types of permafrost Yedema. There's not enough data on it to look at what is thawing, what comes out of the thawing Yedema, how is that impacting our water systems and waterways. Next slide. You can skip this one. That's a really great permafrost atlas. Wildfire carbon emissions. This is a chart that looks at how much carbon emissions have happened in wildland fire, and it ends in 2021. And so the data that we have from wildfire emissions and the impact of wildfire in the north is really underfunded and not current. And there was a study done recently on the Yellowknife fires that occurred in 2023, and it showed that 50% of the arsenic released into the air came from those Yellowknife fires. So the air quality concerns with wildland fire, its effect on permafrost and stability in the north, its global implications for what it's putting back out into the systems. And we don't have enough data and current data to look at what those impacts actually are. Next slide. These are just some examples of maps that have been done. The top one is the Earth. You can see the continents on it. And that was done by the Balfour Center. And it looks at the percentage of warming in the north as degrees, or in the world as different colors. So the bright red is the highest level of warming. And it's also done on a gradient level. So you can see how much more the north is warming than the rest of the globe. Next slide. This is the last thing I'll mention. Arctic observing or local observing networks. There's a lot of local observing networks in the north. This is one that's done through the UAF's Institute of, so IARC, Institute of Arctic Research. And local observing networks and partnering with Indigenous communities can lead to a really in-depth, long-standing collection of data, and also give you the perspective of, traditional knowledge and history of that region. And so there's a lot of local observing networks that are in the north in different communities. Next slide. This one, the AOK network, you can see which communities they work with. This is some example of this scientific data that they use in collaboration with the local observers. And really, as scientists, you get funding to go into areas for certain periods of time. People live there all the time. If you form relationships with people and you have them helping you collect this data, the ability to be able to monitor large-scale changes over time, and also rely on people to say, hey, this is something weird that I noticed, something that you wouldn't think of because you haven't lived there your whole life, would be critically important. Next slide. So I kind of will just leave these here, but I think with the ICARP4 planning process and looking at planning for IPY5, the ICARP4 planning process included an Indigenous, a standing committee on Indigenous involvement. And then recently, a lot of their discussions have been, how do we work more with local Indigenous communities? And I think that's something that IPY5 should really include and consider. Masi.
Thank you, Lisa. And if you want to have a seat over here, great. Okay, we're going to move on to our next and last speaker of this session. This is Dr. Jeremy Wilkinson. He is an expert on sea ice dynamics, thermodynamics and mechanics, ocean wave propagation through sea ice, and deep convection and water mass modification. He represents the UK on the Arctic Ocean Science Board, the International Arctic Science Committee, the Marine Science Working Group, and is a member of the Program Advisory Board for Arctic Science for the UK funding agency, NERC. And I think I forgot to mention, but you probably can guess, Jeremy is at the British Antarctic Survey. In addition, Jeremy is regarded as one of the world's experts in the use of autonomous underwater vehicles in polar oceans. And so I'd like to thank Jeremy for joining us, and you're welcome to proceed.
Thank you very much. It's a pleasure to give this talk. I thought long and hard about what to deliver here, and I think what I've tried to do in the next couple of slides is just really give a personal approach.
Hang on, Jeremy, if you could hold off just a second. We're trying to fix some audio on our end.
Okay.
All right, can you try now?
Yeah. Is this better now?
No, we still can't really hear you.
Any better now?
Only very quietly.
Okay, let me see. I'm not sure what I can do from my end. I can try
Yeah, I'm
and
not
talk
sure if there's anything you can do on your end, but worth a try. Yeah, it's on.
Are you by any chance using headphones?
No, not at all.
Oh, okay.
I don't think anyone will be able to hear it, and I think it's on his end.
Mic volume.
I'm just moving my mic volume up. Is that making any difference?
Yeah, if you move your mic volume all the way up. we're
Okay. Does that
significantly
make it
clearer.
louder and louder now?
A little bit more.
If you can do it a
I'm
little
right
bit.
to the top.
Perfect. That's perfect. Thank you so much.
Okay, that's good. Shall I crack on?
Say yes.
Yeah, okay.
Yeah,
So
go ahead.
thanks a lot. Thanks a lot. Sorry about that. Yeah, so when I asked it, I thought long and hard. I've been lucky enough to be in my career to be involved in a number of projects that have had or designed to have to address some of the societal challenges that the polar research throws up to, I guess, communities around the Arctic, but also out with the Arctic. Next slide, please. So it's amazingly challenging, I think, for us as scientists to address some of the societal needs and some of the challenges in that, I guess, Arctic and Antarctic research throw up. And that's because when you're trying to address these societal challenges, they really need to bring in a lot of different sectors that are beyond the academic disciplines. You've got to bring in the private sector, governmental agencies, Indigenous peoples. If you're up north, we just heard from the previous speaker, local communities, and then you've got the regional and local and national, international decision makers, NGOs and the like. And in my experience, certainly, again, it's personal experience, but thinking from the UK perspective, our funding agencies in the UK aren't that well equipped to engage with that broad sector of community outside academia. And that's because if I think of NERC, which is the Natural Environmental Research Council, they're really driven by funding the best science that they can fund. And that through that program, the societal needs is secondary, that it's always on the review process of the science itself. They do have occasional thematic projects that are driven by a societal need, but generally it's science excellence that is the driver behind that funding decision. We also in the UK have different funding councils. So we have the Natural Environment Research Council, which funds the physical sciences. We have an engineering research council. We have a medical research council, social science research council. And it's really hard to get things funded that cross across those different silos. So if you have a project that involves 2 or 3 different sectors, say medicine, engineering and physical sciences, it's really challenging to get that funded here in the UK. And also our funding agencies, the way they're set up is that for you to apply for funding for these agencies, you need to have a permanent post in a research establishment, either a research institute or a university. So that cuts out a big part of society that you're trying to address or help to address a particular challenge. The next level for us on this side of the pond in Europe is European funding, and that's what I'll talk a little bit. They have a little bit different way of address, and I think the way that they address these societal challenges actually works quite well. Next slide, please. So within, as you know, the European Union is made up of a number of different European states who've all come together to overcome various challenges and work together in a very, very collegial way. So with respect to funding in the European Union, you have you have many funding agencies. You have the European Research Council, which is very much dedicated to blue sky science, a little bit like I said NERC is going for, but also you have these different framework mechanisms where European science has a number of calls that come out, and those calls are to address different societal challenges. And I'll just dig a little bit deeper into those, where those calls come from and the different frameworks that are around those calls. So the frameworks they are evolving process. You have a framework, we're up to Horizon Europe now, but they've started over the last few decades and they change through every few years into a different framework. And that framework is the way they encase these different calls which address the challenge. So a call might be, let's say, something like, what is the socioeconomic impact of sea ice loss, for example? So that call will come up through the system, and then it will be sent around to all the partner countries to adjust and to refine. So for example, Norway might look at that particular challenge differently to Greece, which might look at that differently to the UK. And now other countries like Canada and New Zealand are also part of Europe Horizon. So they have a look at different aspects. So that call gets refined. Those comments from each of those partner countries get sent back to the Commission, and they refine that call, and eventually it'll come out with you to address a number of challenges that these countries think that we need to address scientifically, or whatever the mechanism is. So when those calls come out, there is a demand that those calls are multi-country. So you can't just address this call by me sitting in the UK, having a couple of my pals, and we sit down and do that and we'll say, I'll address this call. You have to bring at least 3 or 4 countries in. Normally it's many more than that. And you can't just do it with one discipline. The way the calls are listed or produced or written is that you can only address that call by bringing in many, many different sectors. It might be working with Indigenous communities. It might be working with industry. It might be working with, say, modelers or biologists or economists. It depends on that challenge of that call, but it's expected that you actually reach out way beyond academia and you bring those experts to the table right before addressing the call, and you develop your program from the start, and that program is co-developed with all those different sectors. The project itself, or the calls, or the project that win those calls, they're different sizes depending on the challenge. Some challenges can be addressed with a few million euros. Some of them can only be addressed by a few tens of millions of euros. And it depends on those calls, depending on the number of partners that you have. Some calls may just have a few partners. Others may have, tens of partners to address that call. But it is very, very much co-designed by those sectors together. And that, to me, in my experience as a scientist, is really, really beneficial, because the way I look at Arctic change or Antarctic change is very different from a person saying but lives in the region, which is different for someone who works in the region, which is different from an economist or a shipping person who runs companies across the Arctic or the Antarctic. So it's, again, to get those different voices across the table is so important. But where I'm, in my opinion, with this
1 minute warning.
Yep, thanks a lot. Where this falls down, I think, is the last bit is where you have the European Union or whatever the funder is, they've asked for this particular challenge to be addressed, but then there's no mechanism when you get your results at the end of that particular project to deliver that to the ministry or wherever you got. So it's expected within these EU projects that you have significant amount of outreach inbuilt into your project to liaise and work with those sectors to address that call as well. So not only do you have those sectors within your project, but also you have many different arms to your project to reach outwards to those sectors as well. Because, of course, once the project's finished, you can't really present it to the members of parliament or your Congress because your funding is stopped. So you have to have those mechanisms inbuilt into your project, whether it's funds to produce a white paper or ministry meetings or things like that. So it's really important that when you do these multi-sectorial projects, you think about the impact and the societal needs and how you get those results to those sectors and make sure it's inbuilt into your project. Oop, next slide, please. I think it's the last slide. So thinking about the IPY, the EU, in my personal opinion, is fantastic because you actually get the best people from 10s, 20s, 30s of countries together to address a challenge. But the IPY is, you're talking about almost all the countries around the planet you can work with. So think broad, think big. Don't think just about the challenges that you develop within an SF project. Think about what are the massive multi-sector challenges that once in a generation can address. And I think Richard did a great job just when I jumped into this meeting about showing what the challenges were that we need as a community to address, because they are massive. So think big about that. If you can, the nice thing with the EU approach is that they have already said what the challenge is. So if a call comes out on, like I said, the socioeconomic impact of sea ice loss, then you know exactly what the challenge and you bring in your sectors to address that challenge. So think again from the US end, And it's very difficult to do that because you don't want to leave people out. But if you actually know what the challenges you want to address, then you've got a better idea of what sectors you can bring to the table to help address those. But of course, with those sectors, you have to actually bring the funding for those sectors. So you need to be able to have a mechanism to fund beyond the academic community as well. So I think that's really, really important. And I mentioned policymakers in your project. They may not be participants in your project, but you certainly have to have that outreach mechanism to build in that you actually engage with those policymakers right from the start. To make sure, think long and hard how are the best mechanisms to do that. And there's been many, many projects that have really good engagement strategies for the different sectors and build on those successes as well. And the last thing I'd say is that for me as a scientist, it would be fantastic. I know different countries through the funding forums are looking at this. If you had an international pot of money where you can actually bid and build those international teams and bid for those international pot of money. But being a realist, it's probably going to more than likely that we will have to work in the national funding frames of each country. We might be lucky enough to have an international pot of money, but more than likely we have those national funding frames. So again, try and work with your funders to try and make sure that you can broaden that tent and bring in those different sectors that you need to bring together to try and find some of the solutions that the polar world can bring to the problems that Richard and others have mentioned. Thank you.
Thank you, Jeremy. Okay, so we're a little bit behind schedule, but we want to make sure we have time to hear from our panelists. So we're going to take 15 minutes for questions. So I'll start off with one from Slido. And I'll read the question. I'll give each of you a chance to respond if you so choose. And whoever wants to go first can go first. Those in the room, please put your questions into Slido so we can get a record of them, get them upvoted, and get them answered. So to start off with, Oscar Schoenfield asks, how do we do outreach as an organized community rather than as 100 individual one-offs? Who do we need to contact or connect with in this new media world? How do we get to speak to those who oppose environmental and earth science? Would anyone on the panel like to share their thoughts?
Jeremy unmuted.
I can have a go at that. That's a great question, a super question, and it is tremendously difficult. I mean, as scientists, and certainly myself speaking, it is difficult to liaise and communicate in a very, I guess, in a way that is open to society and portrays some very complex scientific topics in a very simple way. So, but there are people that can do that really well, and I think it's reaching out, knowing those people, knowing those communities that can work into the sectors that you want to work. So I think it's maybe reaching out beyond science. Don't rely on just on the scientists to portray our knowledge. Actually reach out, and maybe there's other people that can use our knowledge and portray. So work with artists, work with different sectors as well. So I think it's building that knowledge base and getting that out to the broader community, which maybe not be up to us as scientists, but we can try and facilitate that by working with these different sectors.
To build on that, I agree with everything Jeremy said. This is one of our number one problems. At the University of Alaska Fairbanks, we devote a lot of time to this. Open houses, science lectures. We never do enough. For example, this summer, we have on June 14th, we have an open house at HARP. If you ever want to see HARP, come visit. We got half the day, but we need to do more of it. There's too much misinformation. There's too much bad information out there. So it's a nonstop, high priority process for all of us.
And I'll just add, so one, I think the question about reaching out as a body versus 100 individual requests, especially when looking at working with Indigenous communities, that's a really big concern because there's only so much capacity that those communities have to respond to that many people. I don't know that I have the answer for that. I think that there was an attempt recently to ensure that Indigenous communities were consulted on how research is conducted in their territories and how those relationships are built through the Navigating the New Arctic. But what ended up happening was then these communities were flooded with this inundation of requests that had to be responded to in a particular way in order for it to be recognized. So we can't dictate those relationships. That's one thing. And then the other thing I would say is one sector I think that would be really important to see if we can build and fund is science communicators. I mean, scientists have a lot of great information. They're not always the best at communicating that to lay people. So science communicators are in high demand. There's not a lot of them, and they're incredible assets to the team. So that's it.
Thank you. The next question we have here is from Twyla Moon. Are there any international models of research funding that do well at sustaining relationships, built relationships, collaborative research so that they are maintained over decade timescales? So not sort of traditional 3-year NSF projects.
Are there?
Oh, yeah. So basically, are there any mechanisms of research funding that would allow you to engage with an Indigenous community and maintain that engagement and not have it lost because a project lost funding?
So I can start. I am new to this academic environment and research environment, and that's one of the gaps that I've noticed since I've entered this. I've had the opportunity to collaborate with a lot of different research institutes, and you know, you get 5-year or 3-year grant funded terms, or you get a 1-year planning grant to look at working with communities, and then the funding stops, and the onus is on you as a research team to figure out how to continue this work that has offered a lot of benefits and mutual benefit. And I think that's a really big issue that I have not seen any larger scale models. I think people reapply. So if you look at mechanisms like NBREs or COBREs, you know, you reapply every 5 years, and if you're lucky, you get those refunded, and those can turn into long-term projects, but it's not guaranteed. And so I think that's a gap on my limited knowledge. I don't know if Bob and Jeremy have anything.
No, there's a few programs, things come and go over the years. It takes a long time to build up trust to work with the community, a long time of funding. So a lot here in Fairbanks, a lot of our researchers make it a priority, but it's an issue. And it's also an issue, I think the question also mentioned international. International cooperation is also an issue. There's from time to time, there's things that pop up, but there's nothing systematically that we can use and count on over long time frames.
Yeah, I would add that's a great question. I agree with the other two speakers that it's a real failing by the science community that we don't have that. And maybe that's something that we could try and solve during the IPY and put mechanisms in to do that. There are some examples where it works really well. You know, the meteorological community have a network of buoys and weather stations all around the planet that's been funded for decades, that the weather services absorb that information on every hour and get our weather forecast to that. We've got the Argo floats in the ocean that does a tremendous job of ocean properties, and that's been doing that for many years. So there are solutions there that we can look at that do some of the physical sciences, but actually bringing long funding into communities is a real challenge. And certainly for us in the UK or Europe, I think we've failed dismally at doing that for a continuous period of time. But it doesn't mean we shouldn't try and work out the mechanisms how to do that. And maybe the IPY, like I said, is one of those formats we can try and say, well, this is a real challenge for us. How do we solve this? And try and put some things in process that we can actually get that long-term funding out there.
Okay, we'll move on to our next question. This is from Hazel Shapiro. This is directed at Dr. Alexander, but of course we'll open up for responses from our other two panelists as well. You mentioned the healthcare compacting for healthcare delivery in Alaska. Could similar models be applied to some research funding so communities could direct research activities for high impact, locally relevant research topics?
I think that's a really good question. I think that's a really interesting idea. There is this paper that's done by Adelaide Herman through the Institute of Arctic Research, and she illustrates the draws on time for tribes and the work that they try to accomplish in a day. So everything that has to happen in San Francisco or Baltimore still has to happen in those tribes and their communities on a daily basis. And you have a fraction of the people to be able to accomplish those tasks. So I think you'd have to consult with tribes and indigenous peoples across the North to see if that's something that they would be interested in participating in, but I think it's a really great idea. And I see Stacy online, and she's from Quarrick. She might have some thoughts on that. I don't know if Bob or Jeremy have anything to add to that.
I know.
No, the only thing I would say is that, the best way forward is inclusive. And so bringing these communities together in an inclusive and equitable way is the way forward.
Bob, did you have any thoughts?
No, I agree. I agree with
Okay.
Jeremy.
Okay, the next question I have here is from Paul Montisano. Data collection from satellites and field campaigns is critical to our science. How can we have the importance? Oh, it just moved on me.
No, it is.
Of these data and the efforts involved in their collection effectively communicated to and recognized and valued by the public?
I'll step in there. I see this as pretty important too. We're about to be pulling down lots of data. I think one of the things to be really important is artificial intelligence, to sort through all this data and find interesting things. Look over different data sets, find connections, connect high resolution data from different locations, and then come up with conclusions or indications or new phenomena, and communicate that to the public. We still have a communication problem to the public, but I think more data and artificial intelligence is going to help us in the time of IPY.
Yeah, and just adding that as well, I think actually developing more citizen science projects that involve remote sensing data. I think, as a scientist, and especially working in the Arctic and the Antarctic, when we do operations, we're using remote sensing to get the best situational awareness that we can have. But if I talk to I live in a small village in the west coast of Scotland. If I talk to the community there about satellites, they won't have much of a clue what's going on or what they're used for. But if they had citizen science projects that were funded that within their community that was showing how you can use, satellites to better understand how to use different production techniques for the land around our village or anything like that. So it's trying to bring those communities into the use and understanding of satellite products and their use in society. So I think these citizen science projects can be quite valuable in that.
And I'll just add to that. I think if you are talking to local people, they may have their own questions that they can't answer, but you have the technology that you're using to answer your questions. So it'd be worthwhile to have a conversation beforehand and say, hey, we're doing this project. This is what we're looking for. This is the technology that we're using. Do you have any questions that you want us to look at? And they may have some. In the region that I come from, we have really large caribou fences that are 15,000 years old. Those can be seen from satellite data. We've done a number of research projects on them, but the community is really interested in the historic and oral history related to those fences. And so that's a way to kind of collaborate for mutual benefit.
Thank you. The next one's more of a comment, but I wanted to read it as well because it's gotten a number of upvotes. This is from Stacy Lukinson. IPOI should include Indigenous peoples in the Arctic and Antarctic. There are many, many Maori folks with PhDs and traditional knowledge about the southern oceans and other relevant areas in polar science, ice, wind, etc. The next question in the list is coming from Craig Lee, and we've talked a little bit about this, but I just want to give the committee a little bit more time to discuss more on this topic. But can you comment on what high priority environmental services in IPY might support? What sectors, right holders, stakeholders might be engaged?
Yeah, that's a really broad question and a fundamental question as well. And maybe it's about looking at observing networks and how we can understand our planet better, and what I guess if I look at the Arctic Ocean as an example, we've got a number of different countries doing observations of sea ice, ocean properties and things like that, but they're not working together in a unified way, and there's a lot of duplication. There's a lot of areas in some work in some areas and not in others. So I think where I would see the benefit in IPY is trying to bring order to that chaos a little bit and trying to unify how we observe the Arctic and the Antarctic in a more coherent fashion. I think that would be if we came out of the IPY with an observing network that not only fits to the academic community, but fits to the Indigenous community, the private sector and things like that. And where that data, access to that data is free and open using care and fair frameworks. I think, again, all those things are part and parcel of a working observing network. And I think that's something that we should strive towards.
And it might be nice to have some key science foci or key areas that we want to work on common problems or focus on common areas. For example, sea ice in certain locations, connection between sea ice and permafrost and weather, and leverage all the satellite data that we can get. Jeremy mentioned the fact that the WMO in the U.S. works together with meteorological data. We need to do more of that, and maybe have a few common themes across the IPY.
And I'll just add, so obviously, I think Indigenous people should be one of the main stakeholders at the table. I think not only just with local observing networks, but with traditional knowledge. So I'll just give one brief example, hopefully, related to wildland fire. So for the last 8 years, my husband has been working with Gwich'in Council International at the Arctic Council level, raising the issue of wildland fire and what that means in the north. And historically, Gwich'in did cultural burning practices, and then those were banned, I believe, in the 1960s. And when we conducted cultural burning, we did it at a time in the season when most of the land was still frozen. And so you would burn off like the grasses and the brush, but in the forest would be protected from the snow cover on the ground. And so the forest wouldn't burn. So you don't get these like large scale fires that what we have right now. But those have been banned. They have not been studied. We've applied for a number of grants related to studying cultural burning and its potential effectiveness for protecting forests, protecting permafrost, protecting Yetima, reducing air quality, increasing carbon sequestration. There's all sorts of questions related to it. So far, we haven't been able to have a project funded to study those things, but are there practices that exist in these communities that can help us solve some of these problems? I think that's something that needs to be looked at and collaborated with. Masi.
Thank you. So we're going to conclude our panel discussion now. Thank you to Eliza, Bob, and Jeremy for your talks and your input. Thank you to all those who have put questions into Slido. I know we couldn't get to all of them, but they are being kept and preserved, and we can perhaps get to them in the future. I'd also encourage all of you to put your questions into Slido and do it early, because one thing that I'm noticing is you might be writing questions just now, but then they might get buried because other questions have been upvoted and are above yours. In addition to that, also make sure that you're upvoting questions so we know which questions would be most helpful to all of you, so that you're getting the most out of this possible. So at that, this is the close of session 1, and we're going to go ahead and move into session 2, and that's going to be moderated by Scott Goetz from Northern Arizona University. Scott uses remote sensing for his research, and he studies environmental sciences. So thank you.
Okay, hello. Can you hear me all right? No? It should be laid on. Got to get the right end of it. Okay, hello everyone. My name is Scott Goetz. I'm a professor at Northern Arizona University. I'm, I guess generally an Earth observation remote sensing person, and work a lot in Arctic and boreal systems, but really other systems as well. I'm joining here from a large meeting we had in Fairbanks, Alaska just last week, from the NASA Arctic Boreal Vulnerability Experiment, which was our 11th annual science team meeting and our final science team meeting. And I know there are people online and even in the room who are you know, thinking from that perspective of where we go next with all this Arctic science work that was supported by this large campaign. Okay, you're having a hard time hearing me in the back? Okay. I've got it right up to my mouth, so I'm not sure what else I can say. We don't have another mic. I'll try this one. Oh, that's a lot better. Okay. Okay, well, hopefully you caught some of that. So we're going to switch gears here a little bit. Our next session is on scientific questions and science to meet multi-domain operations needs. And by multi-domain, we mean across disciplines and some of the various themes we've been talking about so far. So this session kind of sets the stage for identifying and exploring research goals that can leverage the span and scope of IPY5 and to achieve transformative advancements in our understanding of the polar regions and for the broader Earth system. So throughout the meeting and in this topic area, we'll aim to identify big picture problems that span multiple disciplines, as well as these large multi-domain operational needs, such as observing systems and forecast centers to inform decision-making across a range of spatial and temporal scales. So speakers in this session will provide examples of research areas and themes where a large effort assembled in response to IPY5 could facilitate transformative advancements in understanding and fulfill significant operational needs. That's our objective for this session. Our speakers are listed here on the slide you're seeing. And we will start with with Jacqueline Osterman. I'm afraid I don't seem to have people's bios. Somehow Andrew had those. I don't know where you got those, but
University and Jackie studies GI with recently a focus on the last interglacial, but hopefully she'll be starting to think about geodynamic mantle convection in Antarctica.
okay, I don't know if you were able to catch that in the audience, probably not. But since I don't have the bios, I just asked the speakers to briefly introduce themselves and give a little bit of their background, and we'll go from there. So.
Sounds
Off we
good.
go.
Thank you so much. Can you guys hear me? Or do I need to change my microphone setting?
We can see. Yep.
You can see and you can hear me as well?
Yes, we can
Okay,
hear.
perfect. Well, thank you so much. It's my pleasure to start this panel. I'm Jackie Osterman. I'm a geophysicist. I work at Columbia University in Lamont Doherty Earth Observatory, and I study sea level and ice sheet change over geologic time. And I have a particular focus on interactions between ice sheet, sea level, and the solid Earth, hence this picture here on the right of the ice sheet with the underlying bedrock topography and the mantle flow underneath. So for me, I think the one key scientific question that my community is trying to answer really boils down to how fast ice sheets will melt. Next slide, please. So I think, you know, the question is how can we answer and advance knowledge on that question? Next slide. So to set the stage, let's think about the two main ice sheets that we have. We have the Greenland ice sheet and the Antarctic ice sheet. Next, then the Greenland ice sheet holds about 7 meters. Can you go next, please? The Greenland ice sheet holds about 7 meters of sea level equivalent ice. So that means if the Greenland ice sheet were to melt completely, sea level on average would rise by about 7 meters. So just to give you a sense of scale. The colors here are the ice thickness shown. And we have on the other side of the world, in the Antarctica, we have the Western Arctic ice sheet next, which has a sea level potential of about, next please, a sea level potential of about 5 meters. And the Eastern Arctic ice sheet is by far the largest ice sheet, which has a sea level potential of about 55 meters. Next. The Greenland ice sheet is located at lower latitudes. That means it experiences more surface warming and hence more surface melting. So the main mode of surface melt in Greenland is of ice loss is through surface melting, with the exception of a couple of important outlet glaciers that are ocean terminating, where there's also significant melt through the grounding zone. Grounding zone is the area where the ice sheet intersects with the ocean, so where the ice sheet starts to float, or the glacier starts to float. Antarctica has not experienced as much warming as the Greenland ice sheet, and Antarctica is also, in contrast to Greenland, located on the topography that is at large areas below sea level today. Next slide, please. So most of West Antarctica, for example, sits on a bedrock that is below sea level, but also significant basins in East Antarctica. And as a result, Antarctica loses most of its ice and most of its mass through melting at the grounding zone. And the grounding zone, again, is where the ice sheet interacts with the ocean. So next, just highlighting some of those key grounding zone regions, both in West Antarctica and in East Antarctica. And as I mentioned, even though Greenland is mostly terrestrial, is mostly a terrestrial ice sheet, there are also some marine terminating glaciers. Next, for example, Jakobshavn in the west, and also another glacier up in the north. So how fast will ice sheets melt? Next slide, please. People have modeled this, and Richard has already talked about the Sarusti paper a little bit. Here are predictions from ISMIP-6. So this is a model ensemble of ice sheet predictions, ice sheet change predictions for 2100 for Greenland and 2200 for Antarctica. Shown is both the mean and thickness change and its standard deviation. So where model uncertainties and spread is largest. And what I want you to take away from this is that the regions where we have marine terminating ice sheets and glaciers, so the areas I marked in yellow before, are the regions where the thickness change is predicted to be the most over this century and the next, as well as where uncertainty, and maybe more importantly so, where uncertainties are the largest. Next slide, please. So the reason for this is because the grounding zone is very complicated. It's in the interactions of multiple spheres. It's affected by the atmosphere. It's affected by the oceans and sub-ice shelf processes. The ice starts to float, so there are complicated ice dynamic processes. Again, Richard mentioned some of those. There is subglacial hydrology, water flowing under the bed and up the front of the ice shelf. And there are complicated interactions with the solid earth as well. So what we need is a better understanding of all of these processes. So next slide, please. So the first, I was going to say, I'm going to sort of present three key directions here to answer this question. Next, the first is to instrument, so to improve instrumentation and modeling of the grounding zone. And I will call this sort of studying the known unknowns. We know this is the region of most melt and most uncertain melt, so we need to better understand it. Next slide, please. And this is a figure that just highlights some of the observing systems that can be used. This is a figure from Eric Gruneau's paper entitled Observations of Grounding Zones Are the Missing Key to Understand Ice Melt in Antarctica. And yes, as I said, it highlights some of the observing systems. Next, and I would just extend this figure to the onshore. So there's also, I think, what we need additional sort of GPS, seismometers, radar on not just the floating ice shelf, but also the grounded part of the ice sheet. And I think we need sort of integration of data, these data and models, because predictions are inherently going to be model-based. We need complementary observing systems, because this is a very interdisciplinary space where different spheres interact. And lastly, I will highlight something this was discussed a little bit in the panel before, the the importance of long-term records and long-term monitoring to pick up trends and acceleration in processes. Next slide, please. The second area I want to highlight next is sort of studying maybe the unknown unknowns, and that is understanding conditions of collapse by looking at the past. I do a lot of paleo work, and I think looking at the times when ice sheets have collapsed in the past and understanding why, this can have the potential to really fundamentally change our understanding of the relevant processes, thresholds in the system that we can't gain from just studying the present. Next slide. So this is a figure from a paper, and this is actually from this year, not last year, from Eric Wolf's paper, where he and his team collected an ice core to reconstruct the ice sheet during the last interglacial. You see the Western Arctic ice sheet was significantly reduced compared to today. So understanding whether this happened, confirming that this happened, and why is critical. Next slide, please.
Okay, if you could try to wrap it up in a minute or so.
Yep, I will. And here I'll just highlight, so I mentioned ice cores as an observations, but I'll also highlight the SWACE 2C efforts to get sediment cores and all the challenges that sort of come with this. So I think there's a lot more potential to collect sediment cores onshore, offshore, not only in Antarctica, but also Greenland, to get at these questions. And the last direction, next slide, I will highlight, and next is to not just look at sort of the unknowns, but also the impact. And I will pitch here to instrument and model, continue to instrument and model the coastlines. Next, this is a prediction of relative sea level change out to the end of the century around Greenland. Coastal change in the Arctic is going to be very different than in the rest of the world. Sea levels projected to fall around all of Greenland. And this picture also shows you the number of tide gauge stations that were used to constrain this modeling, which is 0, because there are no datum constrained or datum controlled tide gauges around Greenland. Next slide, and that's my last one. So this shows you here the global tide gauge network. And I would argue that it is very much underserved in the Arctic. There's no, and again, these are just the datum controlled gauges. There are none around Greenland. There are some definitely in the Arctic, but a lot of them are black, which means there are no data, or all the data come from before 2005. And tide gauge data combined with nearshore bathymetry, benthic mapping, I think is an important area and one that has the potential to also engage local communities. And I will end here, and I'm happy to take any questions in the panel later. Thank you so
Okay,
much.
thank you, Jacqueline. Just a reminder for those online and in the room to put your questions in Slido, please, and we'll come back to those. Our next speaker is here in-house, Allison Janis. If Allison, you can come up. And I give it this one, maybe?
Yeah.
Okay. Okay. Hi, everyone. I have to apologize in advance. I've been beset by allergies this last week or so. It sounds like a lot of people in this room are with me on that, but hopefully I can get through this okay. So I wanted to bring to you today the geospace perspective from the space weather point of view, because I know that the vast majority of people in this room and online are not familiar with space weather and how this integrates into the idea of polar year and polar science. So that's really what I wanted to communicate to you today. Next slide, please. Yeah, so the big idea here is that for us and how we see it is that all the energy from space comes into Earth at the poles. Okay, so this is a view here from Laundal, the Nature paper, showing the aurora that exists at the northern hemisphere and at the southern hemisphere. But really, when we're thinking about the energy that comes in and impacts Earth's atmosphere and even down to the ground, we're really thinking about the majority of that coming in at the polar regions, and then sometimes from there affecting lower latitudes as well, but definitely centralized in those polar regions. And so the Arctic and Antarctic is central to what we do and how we study our science. Next, please. So the solar wind that blows from the sun is really where the energy originates from. It impacts our Earth's magnetic field, as shown in this video here. And that energy can transfer from outside the Earth's magnetic field to inside the Earth's magnetic field. And then some processes happen in the interior there, but it can basically shoot that energy towards the poles of the Earth because that's where the magnetic field lines intersect with the Earth itself. And so you're seeing here the aurora that's just been produced by one of these maybe solar storms. But that gives you the example of why we're interested in the polar regions and why those polar regions are so important to our science. But I want to bring it into the perspective of how it affects society. So next, please. And the biggest thing that I want to talk about today is communications. So space weather can be very disruptive and even fatal to our communication systems. Next, please. So we are interested in understanding if we can forecast and predict space weather, maybe on the level that we're able to do so for terrestrial weather right now, so that we can safeguard our technologies in space and the communication that provides access to people on the ground in the polar regions especially, but also around the world. So next slide, please. So this is a schematic of exactly how the disruption of GPS and communication takes place. When you have solar driving events, they can really change the upper atmosphere around Earth, and that can change the way that signals propagate through that atmosphere from the satellites and then down to your farming equipment or your ships or your cell phones or your satellite receivers in your indigenous communities, all of this. And a lot of you have heard some about radio blackouts that have happened as a result of solar storm or disruptions in farming, for example, that have happened around the Midwest from our last huge solar storm back in May 2024, a year ago. But those are all examples of communication disruptions that we see quite often, and we want to understand those better so that we're not left isolated and in the dark. Next, please. So I'll have a list here of what those includes, the disruptions. And the first is loss of GPS lock, which again can affect shipping and military communications as well as farming and you just driving around in your car, for example. Next, GPS errors, which say that your location is different from where it actually is. Next. Loss of communication signals in other areas, so cellular signals, satellite internet link, and military communications. And next. Temporary or permanent loss of satellite functionality. So even out there in space, those satellites are vulnerable to solar storms. And we've seen things like loss of functionality completely from those satellites where they're just kind of considered to be dead at that point. And next, please. So we need to understand the near Earth space environment to improve that space weather forecasting and prediction, and that's the way that we can safeguard these types of communications. Next. So this is a larger figure that shows many different effects of space weather on technology across the world. So not focused just on the polar regions, but I do want to point out some things here that include things like transpolar flights. So there's a little airplane there in the upper center. And that airplane that goes across the polar regions from country to country, those can often be rerouted because they're endangered during solar storms. And so we want to understand if we can predict that a little bit better, we can have a serious effect on the aviation industry. And then there's also things like GICs, geomagnetically induced currents, which I don't really have time to talk about here, but those affect communities, especially at the higher latitudes. Okay, next, please. All right, and I wanted to bring it into science for a second. So this is how we are relevant to atmospheric science. So there is a huge tie-in, and I'll next talk about the observing platforms that are relevant to both of our communities. But how our science is important is shown in this really busy schematic on the left here, where we're showing lots of energy and different forms of particle populations coming in from space. Those are the big arrows going in. But what happens when we get precipitation or particles raining down from space is they create chemical constituents in the upper atmosphere, such as nitric oxides and hydrogen oxides, and those are the green dots kind of scattered around everywhere. And the NOx especially has a very long lifetime in the polar winter, and it can circulate downward, especially during strong polar vortex events, and reach the stratosphere. And when it reaches the stratosphere, next please, it's very efficient at eating ozone, okay? So that destruction of ozone is in part because of space weather events. And we are trying to understand better how the space weather effects turn into atmospheric effects and how that can inform our whole atmosphere modeling. And if you hit next, please, I'll just show an example of a higher energy electron that can deposit energy directly into the stratosphere and create NOx down there immediately. And next, please, a lower energy electron, which creates the NOx upper atmospheres layers, and then that can circulate downward. So there's kind of two different effects, but they all lead into this stratospheric ozone loss. And then next, please. So we need to understand the atmospheric effects so that we can help contribute to whole atmosphere climate modeling. Next. Okay, so there's a lot of stations that we have for polar observing right now in the Antarctic and Antarctic. This is a figure from Alfonsi et al. 2022 showing many of those, but I wanted to talk about how they're relevant to both the space and atmospheric communities. So next, please. I've got a list here of all of the stations and types of observing modes that we use that have relevance to geospace and atmosphere. So I'm not going to walk through these, but you could take a picture, or this will be on the recording later, so you can go through this. But GNSS, rheometers, auroral imagers, and ionosondes are relevant to both geospace and atmosphere for many different science applications. So we can join together to be more powerful when we want to advocate for these dual use networks. Okay, next, please. And my last slide here is, again, hitting on the multi-domain operational needs. This is how we can use shared logistical support to maximize science impact. So here, this is a nice list of things put together by my colleague, Mike Hartinger, about how we can utilize both communities, atmosphere, and geospace to get to these regions where we really want to have access. We can coordinate flights better. We can have more field campaigns and more scientific traverses if we have the need coming from both communities. It makes it stronger, and it makes it more urgent for the funding agencies. And we can also widen the number of possible international collaborations because we've got lots of different research areas. We all know different people that have different stations and projects going on in these polar regions, and we can hopefully work together and share those resources to be more impactful together. Okay, thank you very much.
Okay, our next speaker is Ted Schur from my home institution, Northern Arizona University. And the rest of our speakers, including Ted, will be will be online, virtual only. Take it away, Ted.
Okay, good morning, everybody. Scott, can you confirm that you can hear my audio?
Yes, we can hear you.
Okay, perfect. Yeah, thanks, everybody. My name's Ted Schur, a Regents Professor at Northern Arizona University in the Center for Ecosystem Science and Society. And so obviously we're here to talk about the upcoming International Polar Year. But this slide shows you, I want to just take a second to think about IPY in the year 2087. And I don't have too many details about that. But one thing I do know is that my grandchildren are going to be exactly the age that I am today, but they're going to be living in a world that's going to be barely recognizable to us. And just for the record, I do have children, but I don't have grandchildren yet. But my point is that, someone that we're going to know personally and care for really deeply will be living in this world, and we'd like to give them a sense of where things are heading so that they can make plans accordingly. Next. So we just published a paper earlier this year describing the Arctic of the future, and that's shown in this map here, and a few key elements that you've heard about. The Arctic Ocean will be completely ice-free in the summer and likely an important route for shipping. Surface permafrost is degraded over large regions, and really there will be no place where it's untouched. And the Greenland ice sheet will still be present, but it's already will have contributed a third to global sea level rise that at that point is about 2 feet higher. So in my short talk right now, I'm going to focus in on the permafrost part of this picture, and that's my research specialty. Next slide. This is an idealized picture of the Arctic terrestrial landscape. And so when I first started thinking about the Arctic, I learned that permafrost was defined by temperature. Next. But over the last decade of my own research, I learned new things that really broaden this point of view. Next. So permafrost is not only temperature, but it's also carbon and ice. And it's really the interaction of these three key factors that control the impact of changing permafrost to people living both in the region, but as well to global society. Next slide. So permafrost contains ice, soil, and bedrock, and this is a picture of ice-rich permafrost, this Yetama permafrost that we heard about. And because this hill slope has eroded, we're actually looking at, we're seeing what it looks like underground. Changes in these structural features that you see here have the potential for important impacts to people. Next slide. We can group these impacts into those that affect the infrastructure, and this is primarily through the loss of ground ice with warming. With the loss of ice, the ground surface collapses, and that affects what is built on top. The amount of ground ice varies from place to place, but excess ice is a hallmark of most permafrost ground. Loss of the ground ice also causes a disturbance to ecosystem processes and the services that people rely upon. This abrupt thaw can shift ecological succession and the rate that these ecosystems are responding to climate change. So both of these kinds of impacts are at a local scale in that the ground ice loss with warming directly affects what is happening at that location. So roads, buildings, other infrastructure that's, as well as the ecosystems, are impacted by the amount of ice in the ground right at that place and how fast it changes. Now, permafrost change also has a global scale impact through the carbon cycle, and these impacts of permafrost don't stay in the Arctic. The large amount of permafrost carbon and its potential sensitivity to a warming climate represents a feedback to the global carbon cycle. So we know that human emissions of greenhouse gases cause the Earth's temperature to rise. These warmer temperatures in the Arctic causes the permafrost to thaw. Thawing permafrost then stimulates soil microbes to break down that organic matter as part of normal soil metabolism. And this release of carbon dioxide and methane back to the atmosphere as respiration causes this feedback loop to warming. So the bottom line of this is that climate change could happen faster than we even think based on this accelerating feedback cycle. Next slide, please. This is a map of sites where greenhouse gas fluxes have been measured. So it initially looks impressive, but only some of these are long-term monitoring sites. This map includes all locations where carbon fluxes were ever measured, usually as part of individual research projects. I could show you similar maps for permafrost temperature and boreholes and active layer monitoring. And the take-home message is kind of the same, that our regional to global understanding of changing permafrost is dependent on a handful of sites that operate independently with scientific collaboration as the mechanism that brings data and knowledge together. Changes in permafrost and carbon cannot be measured solely by remote sensing, but instead they rely on direct measurements to understand the changes that are occurring below ground. Monitoring carbon emissions is similar to a storm warning system. We might not be able to change the outcome from these sites, but providing knowledge of how fast the system is changing brings benefits to society, as we can know how much and how fast we have to act and how we have to adjust our policies accordingly. Next slide. I just thought I would put up a few discussion points, either for the end of my talk or later, relating to permafrost. The first is that this carbon feedback, it's likely the issue that's going to grab the attention of the most people. So as a society, we have to grapple with these emissions as we attempt to slow global warming. Next. But the measurements and approaches that we use for carbon are also going to help local people and ecosystems adapt to changing permafrost as well. Next. Now, these ground-based measurements that I've been talking about, they're going to need to be scaled with remote sensing and with synthesis science. So there are real opportunities for permafrost to intersect with other domains of the polar regions that we want to understand better. Next. So in this realm of changing permafrost, we're also going to have to push towards breakthrough science. Some of the ways that we measured permafrost in the past might not even work again in the future as things change, and we need science research to find potential paths forward. And then lastly, something that we've heard about a little bit is that, open science has really moved knowledge forward at an incredible pace, and we need to find ways to make sure information and discoveries continue to be shared among scientists so that we're best positioned ourselves and for society as a whole for this future that's already arriving now. Thanks very much, and Scott, I'll hand it back to you.
Thank you, Ted, and perfectly timed. Okay, our next speaker is Shayna Wisdom from the Alaskan Ocean Observing System. And Shayna, if you wanted to say anything a little bit about your background before you start, appreciate it.
Yeah. Good morning from Anchorage. Can everyone hear me fine? Okay.
Yeah, we can hear you.
I'm the executive director for the Alaska Ocean Observing System, or AOOS, and I've been here just a little bit over 4 years. And prior to that, I was an environmental consultant for 20 years and did a lot of Arctic program management, logistics, particularly related to marine mammal permitting. So I have a lot of experience in working in the communities across the Arctic. Next slide, please. I just wanted to give an overview because we're, AOOS is a funder and we're a convener. So I wanted to make sure everyone kind of understood how we're set up. I won't spend a lot of time on these slides. There's a lot of text, but we're a NOAA funded program under the National Ocean Service. And we're one of 11 regional associations across the US. And we've been here since 2003. Our mission really is to increase observing and forecasting in all regions. So all of the work that's going on, we're really feeding into all of this type of observing and forecasting. And we have a board that is federal and state agencies, and I'll have a slide on the next slide to show you the breadth of our board. We operate as a nonprofit organization. And the key here, and you'll see this how I kind of wrap this up, is the partnering is essential for how we have a successful ocean observing program in our region. Next slide, please. So I won't read all of this, but the point of this is we do have an AOOS board with representatives from all of these different agencies, state, federal, industry, research, environmental, and indigenous. So these are all leaders within these organizations. So the point is we have a lot of connections. We have a lot of board members that are really helping drive the funding and the convening that we're doing. So if there's connections that are needed, we're a good source for that. Next slide, please. So how do we do the work we do? Because we're trying to cover the largest coastline of the US. with the most extreme different ecoregions. We do this with a lot of approaches. We have sustained observations and assets like eco moorings. We fund a lot of work with the gliders with Seth Danielson's lab, high frequency radars that are deployed in the Arctic. We have ship surveys. We like to fund and test new and innovative technologies, things within the coastal hazard, specifically low water level sensors, hydroball, et cetera. We now have 2 imaging flow cytobots for harmful algal blooms. One of the programs that we're really proud of is the Backyard Buoy program, where whaling captains are deploying SOFAR ocean spotter wave buoys across the Arctic. We also have collaborations and partnerships to find solutions, and I'll talk a little bit more about that. And then we work with ocean users to collect, use, and show information in meaningful ways. So we have a data portal, we have response tools, dashboards, et cetera. So we're really trying to be involved in all of the different systems so that we can be effective. Next slide, please. I wanted to point out our collaboration networks. One of the things that we do is really try to bring everyone to the table, making sure that everyone has the information, bring everyone together, reduce redundancy, and this includes the communities. We have the Alaska Harmful Algal Bloom Network, or AHAB. We have the Alaska Ocean Acidification Network, the Alaska Water Level Watch, and then we also co-host the Alaska Marine Policy Forum with Alaska Sea Grant. So I have the links on here so that when the slides are shared, everyone can access these. Next slide, please. We also have a huge data source here. Our Ocean Data Explorer at AUS.org has over 3,000 data layers. We have AUS funded projects, real-time sensors from across the state, moving platforms, data rescue projects. You can use this portal to search with keywords. You can download data and comparing different data streams. It is quite complex. And so if there are people are having struggles trying to find something, please reach out. If you need something, we can help you find it. We work really hard to make sure that hard to find data sets that aren't really archived anywhere else are stored here. So it's a huge resource that we're really trying to make sure everyone's aware of. Next slide, please. Some of the other data resources that we're really working on, because that data portal is bandwidth intensive, which makes it tough for community members and others, based on what you just heard from the previous speaker of comms here in Alaska. We have a Backyard Buoys Wave Buoy app. So those SOFAR buoys that are deployed across the Arctic, and we have a few more going in Quinnahock this year. This app was designed by the University of Washington. It is now live, so it's downloadable on any of the phones. It's really easy to use, and anyone deploying SOFAR ocean wave buoys, and I believe Jim Thompson's group is deploying Swift buoys that are also going to be shown on this app. It's really easy to use. We have it shared across the state. Everyone's using it to be able to kind of roll over in their bed, check their phone, see if it's safe to go out that morning. We're also working on putting all of the important mariners information on both on a desktop version and a mobile version. So it's data streams that we're funding, but it's also all of the other data streams coming in that make it one spot to look at. And we're continuing to work on more products as long as our funding stays stable, and would love feedback. Next slide, please. Again, these are busy slides, but we have a lot of programs we're trying to work on. These are some of the key Arctic programs that I wanted to make sure everyone is aware of. And these are ones that we would like to see continued funding. And we're not the only funders in this. So again, these are partnerships that we do that really work with a wide swath of people. We have the Backyard Buoy program that I just talked about, the Sea Ice for Walrus Outlook, and that has been through ARCIS. We took that over, and we're hoping to continue to find funding for that. But that is looking at sea ice prediction movements and observer support throughout the walrus area. We have the Arctic Watch program, where we're partnering with Marine Exchange of Alaska and COERIC for real-time vessel management system in the Bering Strait. Skipper Science, partnering with Aleut Community of St. Paul Island and Alaska Conservation Foundation. And this is working with locals to collect oceanographic information by fishermen and observers. And then the AOK program, partnering with UAF and Alaska Arctic Coastal Community Residents, Nalakuk in the Cusco Bay, using salmon drones to count salmons and buoys and drifters. So one of the things I wanted to point out in this is all partnered, you notice here, with Indigenous partners of some level. So it's really, we believe very strongly in working with the communities to make sure that they're getting the information that they need where they live. Next slide, please.
Okay, Shana, if you could try to wrap up, please.
We're almost done. Few of the assets that I wanted to make sure you're that are in the region, the high frequency radars, the Alaska Water Level Watch, and then the weather stations on AIS receivers. So there's some assets that we have in the Arctic that everyone should be aware of. And final slide. We're a convener connector. So just wanted to make sure for our role, use of existing collaboration networks, we're connected with a lot of the other groups, and we have this large data portal. And we like to find creative ways to be impactful with our funds. So hopefully, as long as they continue, we're still going to be here. Thank you.
Okay, thank you. Our next speaker is Jacqueline Grebmeyer from the University of Maryland.
Yes, hi. Thank you so much. I'm calling from out of the US, but so you might hear some hammering at the place I'm staying. But I'm a professor and a biological oceanographer at the University of Maryland Center of Environmental Science. I am interested in pelagic benthic coupling, polar biological ecosystems, and in observing systems. So my particularly what 3 points on the bottom is I want to cover some ecosystem status and change. I think this is real important to include the biology in that. The need for time series ecosystem studies through both national and international collaborations, and shelf to basin Pan-Arctic collaborative studies. Next. So why are ecosystem studies important? I think we probably all know this, but we know that sea ice extent and seawater is reduced and seawater temperatures are warming. We have coastal erosion. We just had a great talk on that. And other kind of physically driven changes that are impacting the carbon cycle. But when we get to the ecosystems, it's a very complex, and it really does need sustained efforts. And this is something that new approaches in 2030 would be really very valuable. And just briefly on your figure, what you're seeing here is that it has different components. The top row are the upper trophic organisms, and I think we'll have a talk about that next. But the second row are what is the drivers from physical oceanography. This is the phytoplankton sea ice algae. So without any ice, we won't have that extra carbon that makes the polar regions, both the Arctic and Antarctic, so productive. Third row, you have the zooplankton and benthic feeders in the water column, feeders, fisheries in the water column, and then the benthos on the bottom. So key discussion points and developments for the IPY, because we are seeing biodiversity changes. So we need studies to evaluate that. We're seeing northward movement of both lower and upper trophic species that are shifting the ecological trophics web. These bring food security concerns for coastal communities as well as commercial fisheries. So changes in fish moving north with commercial fisheries going north and competing with some of the larger organisms, especially the whales and seals that are using those really productive areas in the Arctic. But also you have harmful algal blooms like Shana was mentioning. These are an ocean acidification or changing carbon components. So all of these will have impacts on shifting the ecosystem. Next. So one of the things, just an example of the Pacific Arctic, you can see the big trophic animals on the lower part of that left figure, but the big animals are reflecting the ecosystem alterations, not only the habitat which they live, but also the fact that they feed up there. They feed in the prey items. They go these long migration distance. So climate change is shifting not only the upper trophic level habitats, but also the prey base that they depend on. And you can see the gears that Sue Moore put together. You got a shifting in the range that I already mentioned that changes the timing. That impacts growth rates and availability of connecting the food supply with the benthic or pelagic feeders. And then we have changes in body type and conditioning. But what the point of that intrinsic response is also is you need to have some experimental evaluations going on, which many of these have to be done on ships. And I would just point out on that Pacific Arctic, you see the humans on the top part of it. So when we talk about ecosystem change or ecosystems, It's inclusive of humans in the poles, particularly in the north, and their food security. And so when we talk about studies, we need to do coastal, regional, and in the Arctic, Pan-Arctic. Next. So an example, one of the activities that are going on and the need that is an output of the previous IPY and moving forward in the next IPY. There's a Pan-Arctic Distributed Biological Observatory. I bring this out because the upper left is the model of which is being expanded to a Pan-Arctic network. Funding by US NSF and NOAA, but also NASA providing satellite projects, US Fish and Life observers. So it's a very synergistic necessity to do ecosystem science. And if you go around from 12 o'clock, you'll go over to the Atlantic sector that's building. And Jeremy was mentioning some of the need for time series long-term observing, and I'm a big advocate of that. And then if you go over to the lower left, you'll see the developing Davis Strait Baffin Bay one. On the right-hand side, during the Synoptic Arctic Survey, and this is an example of the national and international connections we have to do in IPY. No one country can look at the Circumarctic or even the Antarctic without having collaborations across countries. And so one of the things that was done you can see the dots on the right, was the fact that these were all the cruises that went out in 20 to 2022, and planning is in progress for 2030 to 2032, which comes right up to the IPY. But the important take home I'm saying is that we picked standard measurements are being done. This is inclusive of physics to chemistry and biology, agreement to do some standard collections across countries. There's a network and steering committees, and this is both of these are outputs and important to go forward in the IPY, I believe. Next, just important to point out the interconnection. So I just want to close out with some of the studies that are important for considering for the International Polar Year 5. They need to be multidisciplinary. When you talk about marine ecosystems, you need to know what the drivers are, how they're changing, how they're influencing the food webs, and importance connectivity to changes that may have a impact to coastal community use or even commercial fisheries. There's emerging observations. We've talked about them, about the warming and seawater decline, changes in composition and changes in the habitat. You influence the carbon cycle, and that have importance for ecosystem reorganization. So trying to model these, you need to have experimental approaches and results. You need both ships to look at moorings, which you can get time series, and on those moorings would be water samplers, biological sensors, new ones that are coming out, such as having genetic eDNA measurements on these sensors, or having passive acoustics for marine mammal, knowing where they are and when they are. Satellite observations, autonomous vehicles are an important way to go forward to get the more of a region to look at more than just the time you can do on a ship. And as I said, the importance of getting new biological sensors and new technologies for sharing the data on a real time and cross-platform. You can look at the international collaborations, I think, are essential to do these standardized measurements. It doesn't mean you can't do specific ones by a nation or collaboration on more processes, but you want to be able to compare and contrast, and ideally put something in line if you have transect lines that can be occupied beyond the IPY in a limited sense, even by national collaborations.
If you could wrap up, Jackie.
Yes. And the last thing, the last 2 points would be the modeling capabilities. I think we need to be able to eventually forecast ecosystem change. And that's right now, I think we do a lot better in some aspects and into the biology. And finally, the inclusion of the early career and established scientists and the members of the coastal community. So the importance of, I think, the ecosystem science in the larger picture is taking the new technologies, address some of these common concerns as we build in activities towards IPY 5. Thank you.
Okay, thank you. And our final speaker, which I believe would be a recorded presentation, is by Michelle Larue. And remember to put your questions in the Slido, please, and we'll go from there.
And just really quickly before we watch the recording, there's a lot of really good comments and questions coming in through the Slido. And we really do want to make this a little bit more interactive if possible. So we're going to try to open it up so that you can start commenting and discussing on individual questions in Slido. So it should be on now, so go for it.
Yoda, Tinakoto Katoa, and good morning. My name is Michelle LaRue, and I'm recording this from Christchurch, New Zealand, where I'm at the University of Canterbury, and I wish I could be there with you in person. My background is in wildlife ecology, and over the past 15 years, I've focused on figuring out how to use high-resolution satellite imagery to learn about animals in the Southern Ocean, particularly the penguins and the seals. So as I thought about this presentation, what I wanted to focus on was using a case study example of how integrating new technologies with field-based and interdisciplinary research can be used to bring more information to the table when it comes to learning about the ecosystem. And so what I hope to do here is to seed some ideas for the conversation to identify big picture problems using an example set of US resources that are being used to address one small question within a much larger framework, which is to understand a fundamental question for decision makers. Is the Ross Sea Marine Protected Area working? So to back up briefly, in 2012, I was part of an international team that conducted the first ever Penguins from Space research, and we used high-resolution satellite imagery that was supplied to us by the National Geospatial Intelligence Agency to us as NSF researchers, so we could use that imagery at no extra cost to us. And during the course of that work, we found colonies new to science. We determined a first global population estimate of about 238,000 breeding pairs, which we have since updated. But we didn't stop there. And we recently reported a 10-year global survey for emperor penguins, including updates on the initial population count. And so now we know that there's 225,000 adult birds as of 2018. We found new colonies again, and we now know that there are 66 colony locations. Furthermore, recent modeling work suggests this is probably reflecting fledging abundance more than anything else. And so these adult birds that we thought we were counting aren't even a proxy for the number of breeding pairs. And all of this is largely because these images are optical, and therefore they're taken in the spring when the sun is up. But of course, technologies continue to advance, and it turns out that emperor penguins are, yet again, the subject of satellite advancements, whether or not the satellite company is intended for that purpose. Except now it's in the form of high-resolution synthetic aperture radar imagery, which is what you're looking at here. And what that means is that we can see the birds in the wintertime. And so these technology advancements have allowed for what I certainly didn't think was possible for quite some time, if ever. And we're now investigating how to estimate the breeding population of emperor penguins for the first time. And again, the only reason this can happen is because of technology advancements and through global collaboration. So while actually viewing the birds from space is a relatively new phenomenon, I think it's important to remember that there are tried and true technologies that fill important gaps in our knowledge with their foraging behavior after they leave their chicks, all the way to where and what time they molt their feathers off. So what you're looking at here is a map of emperor penguin tracks from 10 penguins we outfitted with satellite tracking devices in November of 2024. So these data not only give us insights to their foraging space use and behavior, but it also tells us where these tags remain stationary. And in that case, it's in the eastern Ross Sea, and that's telling us where they molt. And after they molt off their tracking devices, they become sea ice trackers. And so with these, small devices, we're learning a lot about the ecosystem by thinking about it in a multitude of ways. And in fact, we still have these 5 devices that are on the ice floes showing us where the pack ice is moving in the Ross Sea. So with these 3 examples of satellite technology for emperor penguins alone, we can figure out almost the entire life cycle now of these birds, including a fine-scale understanding of their habitat, how they move in the ocean, how deep they're diving, and how they may be moving among colonies when they return to their colonies every year. And so this is just one example of a set of questions about one bird that comprises a much, much larger and what I would consider a wicked problem within the Ross Sea, which is the attempt to learn how the largest marine protected area in the world is doing. Is it protecting large-scale ecosystem processes and biodiversity? Is it doing the job that it was intended to? And so the way to answer these big questions, I think, requires investment and access to technology, as well as collaboration among researchers around the world. And so to this goal, some colleagues of mine and I are in New Zealand and in the United States have teamed up to begin sorting the who, what, and how we may begin tackling this kind of very large question. And while we're at the start of our journey, I like to think that this could be a discussion point about a very large question that IPY5 may be able to help address with a specific example of how US-based resources like satellite imagery can help just one of dozens of questions that make up this kind of goal. And so with that as the premise, thinking about satellite imagery, thinking about international collaboration, I will end my presentation and offer to take any questions by email if you happen to have any. And I would again like to thank the National Academy of Sciences and Engineering for this opportunity to present to you today. Thank you so much.
Okay, we covered quite a lot of ground there, and we are running a little bit over, but we have time for questions. But before we jump into those, there's just there's a question in the agenda about what other key topics could be explored during IPY5 and what operational needs might they address. So please keep that in mind as you are interacting on Slido and during the Q&A. So we have a number of questions. And I think the one that rose to the top was to Jackie, or one of the two Jackies. But I think any of the panelists should feel free to address it. But so it's from a modeler's perspective, what do you think is the biggest observational gap that prevents us from better quantifying how fast the polar ice melts? And I suppose we could say, or the permafrost thaws, and other questions related to modeling. So maybe we start with Jackie.
Sure, yeah. So I would say that it's observations related to the grounding zone. And those can come from, the oceans, ice dynamics, also the solid earth. And I think someone also pointed out in Eric Gruneau's paper, he also argued that the sort of ocean circulation part and instrumenting the ocean as a subshelf and the ocean topography is one of the most critical gaps. I'm not an ice sheet modeler, so I can't speak to sort of the ice dynamics. Maybe Richard Alley has a thought there, but I would also say on the solid earth side, the other observing system that is continued to be our biggest resource is just long-term GPS observations, and some of those are at risk of being decommissioned. So having long-term records is really critical.
Thank you.
I'll take on the other one because it
Jackie.
wasn't addressed to me, but I answered Jackie's when I saw it. As I think rate measurements are important for the modeling. I think that's a limiting part for ecosystem modeling right now. And also there's regionally, there's some high intensity areas, particularly on the shelf, low in the high Arctic basin, but that's where the Central Arctic Fisheries Agreement, and we have some ability we need to get some further information on what these changes are happening, like along the slope of the basin, but we need process experiments to be able to put in those models.
Thank you. Any other of the presenters want to take this question on?
I'll throw out something from the permafrost realm. Maybe it affects terrestrial ecosystems at large. And maybe I would say the observational need that really help modelers would be the distribution of ground ice. We know it's heterogeneous and hard to observe because it's below ground, and that's a big feature of ecosystems that influence how fast warming propagates. And so that's probably a big area where IPY could make an impact, kind of understanding the distribution and amount of ground ice that will help all sorts of terrestrial ecosystem questions for modeling.
Thank you, Ted. Anyone else? Okay, we'll move on to the next question, which is from Duncan Young, and he's asking, trends seem important and IPY5 is only 2 years. Are there key IPY4 and IGY, International Geophysical Year data sets that should be remeasured? We'll just open it up to whoever wants to take it on.
Maybe I'll say a quick thing and pass it along, but the definitive answer for all this is yes. And there's great reports out of IPY4 kind of across all these domains, or many of them, that I could imagine having a remeasurement is, a decade or more later. And so I think that information's there. Scott, you also mentioned other programs like the NASA Above project, and there's certainly others in different fields that would be really helpful reference points as we kind of build these time series out. Thanks.
I would just add that I think that, came from IPI is the time series that are 10, 20, 30. We're starting to build them up 30 to 40 years for biological results in certain areas, primarily on the shelf. So I think looking at some of those, and then also trying to make it more inclusive on the Pan-Arctic sense. The other thing I want to say is one of the things on cryospheric work and keeping track of what's happening with the sea ice and the glacial is the connectivity to the network of ocean worlds. I mean, looking at planetary systems, because there's experiments on terrestrial Earth that can be valuable to use for planetary science. So I think there's connectivity that we can get from certain samplings that would be important across disciplines.
I can add to that. I think a lot of you know that the Earth's magnetic pole shifts over time. And so from the last IPY to this IPY, we've seen a change in where that north magnetic pole is, where the south magnetic pole is, and that affects where the energy comes in. But I think it also affects things like how some of the marine ecosystem uses that magnetic field to migrate and to find their location. So it's kind of, again, dual use space interests, but also marine ecosystem interests as well.
Okay, thank you. All right, I think we can keep going here. I'll just keep going until they cut me off. Okay, so the next question is from Russell Schomburg. What types of equipment and technology are underdeveloped or underutilized for in situ data collection? To whoever would like to take that on.
I can just amplify Andrew Lloyd's response there. So lightweight batteries and just better options for data transfer back from observing platforms, also platforms from that incorporate more multiple instruments, GPS, seismometer, weather station, so to have that kind of integrated measurement platform.
I can answer that. One of the things that we've done is work with groups like the Marine Exchange of Alaska, who's putting out AIS receivers across the coast so that we're tracking vessels. We're basically turning those into Christmas trees. We put as many sensors as possible on those. So that type of kind of like what Jackie just said, of making sure that we're including multiple sensors on locations, especially ones that take a lot of logistics to get out to. And then add on to that is making sure that we're training the local people on how to work with that so that we're not having to send people out there to do it. The people in the community can get paid and then learn how to do that so that it's kind of both workforce development and continuing to collect sensors from all kinds of different data.
Okay, is there anyone on any of our speakers that haven't had a chance to address the question yet? I think all of you have responded to at least one of them. Okay, we'll do at least another one here, and this is actually from Andrew in the audience here. Flipping one of the previous questions, what processes or behaviors are observed that are not currently captured in Earth system models that should be or need to be?
Maybe I can say something from the terrestrial ecosystem permafrost point of view, and I think it's a process. Maybe I mentioned we wanted to know where that ground ice was that's underpinning tundra and boreal ecosystems, and then how that changes as things warm. And so the big models do well, sort of this air warming propagating into the soil, but as soon as you have this excess ice and you have these what we call abrupt thaw, it's something that we observe on the landscape frequently, but the models have a hard time doing that, especially at that scale that was mentioned, the Earth system model. People, especially in the Department of Energy NGE project, have made progress kind of at a local scale, understanding that, but you're limited both how you model the process and then whether you have the initial condition right, which is like, where is the ice right now? And so both from the observation and kind of the process, the function of the model itself are areas that could be improved in the next IPY. Thanks.
And I would say the same thing in that the large models don't pull it. There's so much regional variability, and I don't think we should be scared about ecosystem variability. I think we should use that as a template of a palette of looking at change, but how to incorporate the biological components that are always changes in phenology, changing the timing. That is something that is probably, to me, as a marine biologist, an oceanographer, how you get that ecosystem response to a level that we can actually move to forecasting. There's certain areas that I work in that is 40 years of time series, and that is something that maybe could be useful. But I think that's a real limitation, is trying to get the ecosystem in these larger models, but they're very important. And there was one other question that came up about weather, about having atmospheric measurements, and it's true. We talk a lot on the ecosystem, but we need to know, I know that Synoptic Arctic Survey, that's always, you have weather balloons and doing weather measurements, because we don't have those, that forcing is extremely important, the atmospheric forcing for that changes that we're seeing in the polar regions.
Okay, thank you all. We have some additional questions here. Some of them are quite specific, maybe to individual speakers. Can I just keep moving? Wrap it up?
No, a couple more minutes.
Okay.
I know that
All right.
there's a question about sharks, and I can't really, I'm not a fisheries person, the impacts of having changes in sharks. So I think the Greenland sharks, some other these, there are sharks, you'd have to talk to a fisheries biologist. And the question was whether or not how the ships commuting through the Arctic and triggering climate change and ecosystem change. I think we do have to consider the fact, I can't answer that completely, but we will have increased transport. We already are. There's a lot of money going into Russia and talks, and every country is building vessels to go into the Arctic. So we need to incorporate that shipping into modeling impacts on migrating species.
Okay, thank you for that. All right, we'll take one more, and this one is to Allison. And the question is, what is the minimum duration a GNSS station would need to be deployed to be useful for geospace applications?
The minimum duration of time. I believe so. Okay. Yep, that's a good question. It depends on actually what you're going to use that GNSS signal for. So most of what we study, we're interested in building up models. So predictability, forecasting. So we'd really like it to be there for a long enough time that we're seeing different phases of the solar cycle, which is about 11 years, or even different seasonal effects, because we see different changes with even seasons, winter to summer and back, and different solar conditions. So if it is there for enough time where we see some solar storms come by, that's most helpful. So I'd say on the order of, months to years is really the best duration.
Okay, thank you all very much. It was a very diverse range of topics we covered there and a fascinating presentation. So I appreciate your participation. And I think I will pass it back to Craig now to introduce us to lunch.
Really important, thanks. So we're about to break for lunch. Just two quick comments before we go. There is a comment wall, which I'm told will be right in front of you as you exit the auditorium. Should be pretty obvious. That is a place to register more thoughts, reflections on what you've heard, other ideas for questions, right? Ongoing throughout the meeting. So for those who are here in person, please use the wall liberally. That will all be captured. I'm assuming there's an online functionality that's similar for the, right, okay, for the Padlet for virtual participants. Will serve the same purpose. That's a great place to register all the thoughts that you haven't had time to put down as we've been going through the sessions. Lunch will be just outside, and when we come back, we will launch into our first interactive activity, which will be a World Cafe. Thank you, everybody. Look forward to conversations over lunch. So kind of, on par, we are running behind, just pretty natural. What we're going to do next is have reports from the breakouts. Hopefully everybody had a set of really good discussions. We're going to have to keep these short to keep us from running even further behind. So I'll call each group in turn, and maybe if you can do it in 3 minutes, that would be fantastic. And then we can continue discussions during the breaks and over beer tonight at Lloyd's. So Andrew, would you like to go first?
Yeah.
All right, can everyone hear me in the back? Okay, great. I will try to keep this brief and hopefully somewhat concise. There's a lot of information here to sort of condense. I'd say that, well, let me just start off by first reading the first question. Oh, I should do that too. So I'm Andrew Lloyd. I'm a research professor at Lamont Doherty at the Observatory. The question I'm reporting back on is, what critical research questions do you think should be considered in IPY5? These could build on examples discussed in the talks or be different. What societal implications and interests might these research questions inform? What types of experts or groups would be involved in addressing these questions? So sort of the big question that I think came out of this was sort of how fast and by how much will the ice sheets melt in the next few decades? This is obviously very interdisciplinary science, as we heard from the talks earlier, involving all of Earth science as well as engineers, many stakeholders and policymakers, of course. Important part of this and other aspects of science, of course, quantifying uncertainties, which we need modelers involved in that. But then also we need the modelers so that they can tell us where do we need to be making observations so that they can improve models, which is a little different than what we typically hear, which is sort of we need observationalists to tell us what processes should be incorporated in models. Other big science questions included things about space physics and the need for observations, in particular in there's lots of observations coming from West Antarctica, but there's very few observations coming from East Antarctica. There was also one thing that was brought up, a focus on understanding ice-ocean interactions beneath ice shelves, and a list of sort of key topics that need to be explored. I don't have time to get into this. The other thing that came up related to society and reflecting and recognizing the fact that polar sciences need to really also include the native peoples in the pole and get their inputs, and they should be helping to drive and form the science as well. There are aspects, of course, in terms of the science related to landscape change, whether that's related to the permafrost and its impacts, more increase in wildfires, et cetera, et cetera. One thing that got brought up that I thought was interesting, I hadn't thought about it, was sort of the human impact. So as the poles get warmer and you have more tourism to the pole, how is that influencing the polar regions? And maybe it's introducing more plastic, more waste, more environmental impact as well. And I think, let me see, maybe one thing two things that I'll just end on real quickly. One, we have these models that are global and they convey hazards or things that will change in a global sense. But we need to make sure that we're also getting that information out at the local scale to policymakers and practitioners. And then finally, the other thing I'll mention, which is that, and this got brought up, sort of the fact that fieldwork can be dangerous for certain groups of people, whether that is physical, emotional, or psychological. And how do we make sure that doesn't happen? And also, how is sort of the sociology aspect of polar science? What is that like? And sort of, you know, sort of the need for there to be studies in investigating that. So happy to talk about this question more, but I'll leave it there with my somewhat incoherent thoughts, but there you go.
Thanks, Andrew. Next, we've got Mary Louise Timmermans, who is online.
Hi, everyone.
Great. Thanks, Mary Louise.
Hi, I'm Mary Louise Timmermans. I'm at Yale University. And so I will summarize. We talked about some pretty similar topics. Yes, we recognized that Indigenous people should be part of IPY planning and talked about a few different examples where there's intersection between learning from Indigenous practices, for example, in long-term permafrost stability. In several themes, we talked about sea level rise as well, how we need to understand the magnitude and speed. We need a project to say what sea level rise will be, and there's never been, apparently, there's never been a large-scale dedicated US project to understanding sea level rise. I think this is really interesting for the connectivity between the cryosphere and the rest of the globe, like IPY, not just isolated to a project that relates to the poles or projects that relate to the poles. And this should include also constraints from paleo data. We had a discussion about permafrost, and permafrost carbon emissions need to be measured much better. And now there are improved technologies for doing this on a large scale. When we have these large scale observing systems, how do we interface this kind of long-term infrastructure that we might set up and develop as part of IPY? How do we interface this with process studies, where we need to understand how processes work better? Also, with respect to the carbon cycle, the IPY initiative can be interfaced with other global carbon initiatives, such as the Carbon Cycle Science Plan. And drilling efforts came up with respect to permafrost. Uncertainty, the other group talked about uncertainty as well. We talked about uncertainty specifically with respect to permafrost and what language can we use for uncertainty with respect to the role of permafrost and feedbacks, etc., so that policymakers and the public can understand. And then observing, how can we leverage tourism and increase shipping activity? We talked a lot about how there's going to be more ships and activity up in the Arctic as the sea ice continues to retreat. How can we leverage that in some kind of observing capacity? And then AI, new avenues that will specifically make use of AI, or that can specifically make use of AI in IPY, particularly with respect to the cryosphere and satellites. Also on observing the fact that sensors are changing rapidly, and the sensor technology is changing rapidly. We're going to see new sensors. Hopefully, we're going to see new sensors, small, robust, cheap, reliable sensors that can bring us a lot of data, and data management is going to be an issue that we're going to have to address. And one final point is solutions. I thought that was interesting. Somebody raised the point, to what extent should we be talking about solutions here? Beyond the science questions, what are the solutions now? And as we all know, the Arctic is already a target for increased geoengineering efforts. in the form of ice growth and so on, artificial ice growth and so on. So solutions is another interesting avenue. All right, well, thanks everyone. I'm sorry if I didn't capture everything, but that's the gist. Thanks.
Great, thanks, Mary Louise. I think there's probably an avenue for written summaries of the breakouts as well, so we'll make sure we get things incorporated. Next up, we've got Ginny Catania.
Hi, everyone. So my question was, what bipolar research questions can be best addressed through an approach that links the Arctic and the Antarctic? And I had the group answer that question first. And so we got questions like, how have the poles changed in the past? And this was anything from how's the polar climate changed? How's the water cycle changed? How has marine habitats or ice sheets changed in the past? And then how might they change in the future? A lot of discussion around what are the similarities and differences in processes at the poles and what can we learn around about one pole that might apply to another. For example, the Greenlandification of Antarctica. How do global teleconnections drive synchronous or asynchronous climate variability in the polar regions? And then we had a lot of discussion around how can we improve sort of the awareness of the importance of polar regions to the populations in the lower latitudes. Sort of related to that is how do we improve how we do science so that it's more equitable, allows for more sustained and meaningful engagement with both communities, but also translating that to better and more equitable international collaborations that allow us to answer questions at a much broader scale than we're kind of normally able to in our business as usual approach. And then I brought up polar geoengineering because it's a bit of an elephant in the room, and Richard had a really good response to that, which I enjoyed. And he said that we really need to address first what are the ethical and social implications of polar geoengineering before we punt it to the research communities. And then we also had a big sea level discussion. And the way that I like how people phrased it was what controls 1 meter of sea level rise. And I added for local coastal communities because I think that then brings it towards more like where people live. And then the second part of our question was what societal implications would these questions inform and what types of experts or groups need to be involved in addressing them? And instead of really answering that question, I'm going to tell you what Martin Jeffries said, which I thought was really important. And he said that we are missing a grand unifying theme and that if we're going to be doing something as big as an IPY5, we need to really be thinking about why we're doing this and who we're doing it for. And that our research needs to be aimed at delivering improved climate system projections globally, and that those projections inform science-informed mitigation and adaptation. And we have to actually deliver something beyond just peer-reviewed journal articles. We need to deliver products, maybe data services or solutions. And really, if we were able to do that via an IPY5, that we would be able to serve an enormous group of people, pretty much everybody on the planet. And so the types of people that are involved in addressing these questions would be like all of our sciences, but also hopefully people who work on coastal processes and coastal residents and coastal communities, including all the sort of government agencies and non-government agencies that are involved in coastal decision-making. Thank you.
Great, thanks, Jenny. Next, we'll switch back to one of the in-person breakout groups. Jenny.
Hi, I'm Jenny Baseman. I'm a member of the organizing committee and also on the Polar Research Board. And I'm currently an international polar consultant. I had the same question as Jenny, so the bipolar connections. And all 4 groups pretty much listed everything, including the kitchen sink. That was important. Ice sheet change and sea level rise, tourism, ocean ecosystem change, permafrost, coupling and interfaces along the whole ecosystem, submarine ocean discharge, the magnetosphere, and looking at the energy entering at both poles was also something that was brought up. Everything sort of surrounding just forecasting change in the polar regions and how that's impacting the globe, ocean currents and beyond. One comment even suggested looking at introducing the polar bear to Antarctica, see how that would go. Teleconnections, of course. A lot of things that we've been hearing a lot about for a number of years. Ice shelf coupling, ocean modeling, improving modeling, needing more observations. Perhaps think about including the third pole in this IPY. One big thing that came out, particularly in the last group, was probably the most important thing is to close the carbon budget, because that's kind of the missing piece. So I thought that one in particular was very interesting, and that one needs a lot of different subjects. Most of the sessions that I was in, we didn't get to the societal impacts. We had more time talking about the science. And when we did get to who should be involved, it kind of came up to be everybody. So it was, I don't think we quite were able to narrow down what we really needed to do. So I was involved in the last IPY a little bit, and I think it's important when you think about the next IPY to make sure you have projects that are unique to the IPY that can only be done during the IPY, because a lot of these things don't necessarily have to be done just during the IPY, and probably will need to prioritize what projects you're going to want to do, because you're not going to be able to do everything but the kitchens, or including the kitchen sink. So just my 2 cents here at the end.
Great, thanks, Jenny. Okay, so we're going to move on to the next question here, which was environmental services and operational needs. And we'll start with Lil.
Okay, so the question, what environmental services operational needs might be needed for IPY5, that question is inherently tied into 2 other elements that we're going to address. The first one is international collaborations, and the second one is human capacity. So to the groups that I worked with, they were absolutely outstanding. I can't say enough. So let's start with an IPY is to think big. One of the comments was that the polar community, the research community, is small. I understand that, but I also disagree when you think about the collective pool of individuals we have, not only on the screen. There are individuals from Texas, South Carolina, Idaho. The polar community, North and South, is actually quite large, and it's even larger if we think about international collaboration, which leads us to the question of what resources are currently available and how can those resources be leveraged and shared more readily. So whether that be the open exchange of equipment and field stations, data infrastructures across all polar collaborations, and data infrastructures that allow agencies and groups to basically look at the risk trade-offs of international collaboration with the net benefits or the net gain they get for science, broadening their knowledge base, and what we get as a global polar community for advancing things like better climate forecasting, better space weather forecasting. So tangibly speaking, better sharing of resources and also leveraging of resources that people don't normally use. So that's lowering the cost of technologies to enable more people to get involved in polar science, ensuring that the groups we do engage operate with other groups that we don't normally engage, such as the Schmidt Ocean Institute, Greenwater Marine Services, and other non-governmentally funded organizations. And also partnering with communities whose contexts are very relevant to their daily lives. So not only do we have services that are more freely shared across borders while mitigating risks of international collaboration, but we also expand the pool and diversity of polar researchers and data that contribute to global polar knowledge, north and south. Oh, and a taxonomy of international collaboration, which I thought was absolutely brilliant.
Thanks, Will. And now we'll get the online perspective to question 3 from Ahu Haman. Hopefully I have it.
Hi. No, Hahua. Thank you. Yeah, I'm Hahua Hamano. I'm from NASA and I worked on the heliophysics big year. And our question was similar to that question. And so, what environmental services and operational needs might an IPY5 driven effort aim to address? And so, our group identified some key environmental needs, including improved climate monitoring systems for Arctic boreal wildfires, long-term ocean monitoring around ice sheets, and infrastructure for accessing subglacial environments. Some of the scientific gaps that require attention, including incorporating carbon flux processes like permafrost thaw into global models and surveying Arctic pollutants. And I think similar to Andrew earlier, knowing the human effects and environmental hazards that are downflowing from some of these ecosystem changes was one of the focus there. What structures would need to be built to provide these services? So data infrastructure priorities included enhanced connectivity for polar instruments, support for indigenous data sovereignty, some unified mapping tools that held those principles of data sovereignty and protection, and also some structures around facilities and organizational frameworks, including coordinating observational platforms like collaborative use of icebreakers and aircraft, with multiple folks mentioning helicopter capability on research vessels, and then leveraging emerging technologies for improved data collection and modeling, which was also mentioned by Ginny earlier. Participants folks also called for expanded research facilities in Greenland, which then led to the need for internationally led infrastructure support. I think Andrew talked about like safety for field research that was included in that discussion. And calling for the need for remote Antarctic base camps for multidisciplinary research, and all of that. Bundled into that was longer term multidisciplinary research. And then beyond physical infrastructure, robust organizational frameworks are needed for those components, including inclusive planning structures, international data sharing protocols, and coordinated satellite data systems, enabling open information sharing among researchers and communities. So echoing some of the thoughts that some of the other groups have already shared. And then what types of experts and groups will be involved in addressing these questions? And so we emphasize bringing together diverse expertise and interdisciplinary collaboration across specialties, from physics to geospace to glaciology. A lot of folks have mentioned the indigenous community partnerships. They are critical, incorporating traditional ecological knowledge and boundary spanning organizations that connect different knowledge systems. Citizen scientists, policy expertise was one that was brought up. That's hadn't been mentioned already. And so early involvement of government agencies and Arctic Council working groups. Yeah, that was it.
Great, thank you.
Thank you.
Okay, last question, moving on to looking at how different research questions could be addressed synergistically. We'll start with the online breakout with Byron Adams.
So our group addressed the question, are there different research questions that could be addressed synergistically using the same or similar infrastructure data sets? And then also what might that collaboration of that type entail? And we found the question a little bit challenging, not knowing what the big, questions from group one were going to emerge. But given that there were really several themes that emerged, first, we discussed how existing infrastructure like icebreakers and field camps and traverse logistics can serve like multiple research domains simultaneously. And some of these ideas included things like autonomous underwater vehicles for acoustic tracking, aircraft with expanded heavy lift capacity, new ice-breaking vessel that's explicitly designed to support multidisciplinary work. We also explored the power of interoperable data sets. So from things like satellite time series to genomics and remote sensing and shared data platforms, especially obviously those that are aligned with the FAIR principles, could be leveraged with things like climate modeling, biodiversity analysis, and even some AI applications that we chatted about. There were some licensing issues flagged, especially for like high resolution imagery like Maxar data, which has already yielded really valuable product like obviously like the Arctic DEM and REMA. We saw really strong support for aligning research objectives across disciplines. For example, like co-locating permafrost monitoring with terrestrial or microbial ecology sampling, or for like merging paleo records and modern processes at shared sites. So co-located in that way. So spatially shared, but temporally like very different time spaces. And then some folks also emphasize the need for global scale synthesis across hemispheres using like shared observing systems and timelines, but doing so like synchronously, like in the like in synchrony. Yeah. We also heard about the critical need to consider human biology and not to ignore that aspect of it. Advocating for science needs and supporting human populations and their challenges. Their needs really are burgeoning, and we need to consider ways in which science can support them directly, like indirect and meaningful ways in which they can see. Some folks in our group also noted some underutilized collaborative networks that have already been built and constructed, but could be used more efficiently. And also opportunities to bring in less traditional partners. So some of these collaborative networks like SCAR, right? It's already been built. It's there. There's the infrastructure. SUS, for example. There are many others. But we're missing opportunities to bring in less traditional partners like fisheries managers, remote sensing developers, and maybe even VR specialists. And involving stakeholders came through pretty clearly here is super important. And if the mechanisms, right? So if mechanisms for shared funding and infrastructure should be developed, could be developed, then that would be a big deal. No, but overall, the ideas from our group suggest that, yeah, if we could align our infrastructure and our data and some of these objectives across disciplines, we could definitely get at some really big and important questions.
Excellent. Thank you for the summary. And lastly, in the room perspective on that question, Jim.
Thanks, Greg.
Okay, hi. I'll do my best here. Jamin Greenbaum, Scripps Institution of Oceanography. There's some overlap with what Byron just said from the groups here. Some 3 examples came up of some projects that were obvious fits for this, like coupling observations of atmosphere, ocean, and ice sheet dynamics, and coordinated surveys, biogeochemistry and ecosystem response to climate change, atmosphere and surface processing interactions as some examples. There was broad agreement that there are lots of opportunities to address interdisciplinary research questions with shared infrastructure, as already has been said, and data sets. Standardized deployments, such as ocean moorings co-located with weather stations, HF radar and biogeochemical sensors, as was done on the above, or the SWARM project, excuse me, was brought up as a great example. These things can support physical oceanography and ecosystem studies. with simultaneous investigations of freshwater fluxes, sea ice change, and biological responses, for example. Sending field teams out with standardized kits, no matter what their primary objectives are, like seismic stations and GNSS stations. Similarly, combining surface, airborne, and satellite platforms, collecting data on trace gases. The above Swarm and Mosaic projects were offered as great examples for very specific locations doing interdisciplinary work. Might be worth, like what Byron just said, considering larger regional synchronized studies. PoleNet was put out as an obvious, wonderful example of a solid Earth experiment turning into a geospace resource, a resource for the geospace community. We should plan for this kind of thing in the future. A couple easy wins that could be facilitated internationally with weird funding situations. Okay, 1 minute left. Could include things like the standardized kits that can go off on whatever expedition. And then projects like what Jackie Grebmeyer talked about with the Pan-Arctic Distributed Biological Observing Network as, the international community picking locations to revisit, no matter where you are from or where your funding comes from, you can just revisit those networks. These are decisions that can be made independent of, other issues. Collaborations require interoperable digital infrastructure. That was brought up as a big issue. Long-term funding, international coordination. Big problem is siloing of projects. This is where the last group just ended and we didn't have more time, unfortunately. But, a big issue with the current status quo is that we have siloing of projects and their results. Why are our existing structures incapable of dealing with this? We need creative ways to break down those silos. Improved digital infrastructure could do that. Better tracking by funding agencies and repositories maybe, but I'm out of time. So thank you.
Thanks, Jamin. So because we have a large number of online participants, we're trying to keep it at least vaguely to schedule. We're going to shorten the break, so I'll have a 5-minute bio break, get everybody back in the room. This has been fantastic input. It's great to see all the thoughtful comments and input to the working groups. I would come back to Martin's comments and the comments about, right, what are we doing and why, the polar regions' roles and climate forecast and climate variability, right? How do we frame? We've got a lot of really great thoughts, right? There are a lot of historic pillars for science programs. How do we put that all into a framework, right? How might we structure it in a way that would argue for these big questions and big programs that we want? Things to think about. Thank you.
Okay, I think we're going to get started to try to keep us moving along. So if everyone in the room could take a seat. Terry, if you want to come up, you're welcome to join us. I will hand this off to you, Brittany.
Hey, there's someone else in person. Can folks hear me okay? All right. Hello, everybody. My name is Brittany Schmidt. I'm a professor at Cornell. And my group, amongst other things, we build underwater technologies. So I'm excited to get to be leading today's session. That's somewhat related. So the session is going to be about approaches and capabilities that might enable IPY5. So the description is the remote, harsh environment of the polar regions presents unique challenges, as we all know, for observational research, which complicates the task of collecting sustained measurements of the necessary spatial and temporal scales and scope. Polar research often requires highly specialized equipment and infrastructure built to withstand these cold conditions, and costly logistical capabilities are required to deploy and sustain researchers and equipment in remote locations. Though largely free from environmental challenges and faced by in situ observing, remote sensing and numerical modeling also rely on in situ measurements, and thus are constrained by the sparse data availability, temporal and spatial resolution challenges, and other issues such as frequent cloud cover, seasonal darkness, and other challenges. And so what we're going to focus on today is that rapid changes in technologies and approaches have occurred since IPY4, and advances continue to emerge that may enable new and expanded efforts in field remotely based and modeling research for IPY5. So we're going to discuss that, and I wanted to really make sure that we focus in on a couple of challenges to these. So we know that extending operations might be one of the key factors here. How long does a particular platform make an observation, whether it's observing platforms that are moored in the ocean, we've got drones or AUVs or ROVs and their battery length, the extension of those operations over many years perhaps. We've got design constraints that really change, right? Mass, weight, and power. And other ways that we might be able to leverage synergy in order to do these observations. I think one other thing that we have to remember is that it is often kind of thought that technology replaces people in the field. And I think really what we know now is that technology makes you better, makes you more efficient, gets you more science. So you're doing more science per dollar with better technology as opposed to just replacing people. There's no real replacement for that, at least at this point in time. So anyway, so with that, let's go ahead and introduce our panelists. So we have a number of people virtually. So we'll start and have each of them. So we've got Matt Siegfried from Colorado School of Mines, Brendan Rogers from Woodwell Climate Research Center, Esme Van Vliek from the Commonwealth Scientific and Industrial Research Organization, Charles Coven, and here in the room, hooray, Terry Wilson from Ohio State. I'm sorry, Charles from Lawrence Berkeley National Lab. So we'll just go in that order and go ahead and let folks, they'll give about a 7-minute presentation, and then we'll have time for some questions with the panel afterwards. So Matt, if you are online.
I am here.
Hello, Matt. Matt is joining us from Teaching Field Camp. So nice vest.
Thank you. Sorry that I look like a construction worker. And I will apologize if I have to run out because of an emergency or whatever that might happen. We're cursed this year. But I thought I would start by just giving you a bit of my background so you understand the perspective I'm coming from. I'm an associate professor in the Department of Geophysics at Colorado School of Mines, also our field camp director. So I've done 9 Antarctic field seasons, mostly in West Antarctica in camps ranging from 3 people to 60 people. These camps have supported airborne geophysics, surface geophysics, subglacial access, so a huge range of experiences out in the field. Driven many thousands of kilometers on snow machines while taking care of what I think is still the largest on ice GNSS experiment with upwards of 50 stations over 10 years. So I deeply understand the problems of power and batteries that Brittany was talking about. But I also heavily participate on NASA science teams. I'm the co-lead of the ICET2 Land Ice Working Group right now. I work on SWAT, STV, IceBridge, used to work on IceBridge, and probably most importantly for IPY, currently a member, science team member of the EDGE mission, which is in the Phase A competition for the Earth System Explorers competition that'll launch later this decade. And so this gives me a bit of a broad base to talk about technologies and observational strategies. And when I was thinking about what to talk about, I thought a lot about kind of where US really can take leadership for IPY on the technology side. And so I organized this somewhat into 3 topics that I'll go through somewhat quickly. Sorry, I don't have slides. I've had a couple emergencies in the past few days to deal with. But I'll talk a bit about the remote sensing aspects that came up a little bit in the breakouts. Then I'll talk a bit about access technologies and finally power technologies. The remote sensing that came up in the last breakout was mostly about licensing Maxar imagery. And that's super important, but I think we need to think much more broadly about the remote sensing technologies that we're going to have for IPY, because there's a strong possibility we'll fly blind if we don't really put in big efforts right now. ICET2 has enough fuel to get us there, but it needs to continually be funded by NASA. NISAR hasn't launched yet. That would be a game changer for us in IPY, but we just saw this past weekend a radar satellite blow up on launch, right? Like we are at a knife's edge in terms of the technologies we'll have access to from space. That might be, we need to think more about private satellite companies. It might be we work deeply with NASA and ESA to spin some missions up. But really, the benefit of space has been highlighted over the past week with a paper that came out that showed just how much snow is falling in East Antarctica, right? We need satellite technologies that can measure extremely fine scale processes over large spatial scales. That basically boils down to we're going to need LiDAR in space. And we have one potential mission that might be launched, EDGE. Obviously, I'm biased and think it should be funded. But if we don't have LiDAR in space, we really need to think about how we're going to do things like measure snowfall and surface mass balance at scale during IPY when we're talking about answering questions about sea level. We also need to know, the flow and changing flow of Antarctica and Greenland and all glaciers on Earth, really. And so that's going to boil down to NISAR, which hopefully will launch later this year. But if it's not, we're going to need a really strong backup plan for how to replace that technology. I'm quickly running out of time. So I'm going to talk about access technologies for a quick bit, because we are going to need boots on the ground to study the processes that we still don't really have constrained all that well. I talked about shear margins in my breakout group, but there are plenty of other places on ice sheets and glaciers that we really need to understand: the ice bed interface, the ice ocean interface, grounding zones, etc. And we need to be able to work safely and efficiently in these unpredictable and, for shear margins, particularly extremely dangerous environments. And so that means making field teams more capable and having more rapid and smarter technologies, autonomous and airborne fiber optic deployments, for example, across shear margins, better in situ robotic sampling. For the ice bed interface, we in the US program have no technology at the moment that we could deploy to Antarctica or Greenland and do experiments at the ice bed interface, which is the whole game for sea level, that and grounding zones. So we really need to think about what our access technologies look like. Hot water drills, rapid chipping drills are super important, and we need to start thinking right now to be able to have them in 2032. We're actually probably a little late for this already and need to play catch up. Finally, power technologies. Anyone that has done polar field work knows that all of your science depends on how good of a power station you can come up with. I probably lifted more car batteries from beneath my feet to above my shoulders than anyone else in the 2010s. And my body knows that that's true at this point. So we really need a step change in how we're powering everything from a single instrument out in the middle of nowhere to work year round, so we're not biased to summer only measurements, all the way through how are we powering these large field camps. What I really wanted to show you was a drone video from the Salsa camp a couple of years ago that showed the infrastructure needed just to access one place at the bed of Antarctica. We had giant diesel generators, right? That sort of logistics capability just is disappearing before us for good reasons and bad reasons, but we're truly going to need to rethink what our power systems look like. I like talking about this as the energy transition for Antarctica. We're nowhere close to successfully doing that sort of transition, and we need to really put a lot of money into what our power systems are going to look like in 2032. That means working with electrical engineers, mechanical engineers, and looking across the world for how remote environments are powering their infrastructure right now. That puts me right at 7 minutes. So I look forward to discussing this more on the panel.
Thanks, Matt. Excellent. All right, so mostly because he's on screen. Brendan, would you like to go next?
Sure, and I did have slides. Oh, great. All right, thank you everyone. It's a pleasure to be here, well, virtually, and talk to you all. I'm Brendan Rogers, going to talk to you my perspective on approaches and capabilities. I'm from the Woodwell Climate Research Center and co-leading a relatively large project called Permafrost Pathways. And I just wanted to start with this map because this is the region that I mostly work in and think about, and we'll have this talk focused on. So it's the tundra and boreal environments, and within that, the northern permafrost region. Next slide, please. So I mainly think about technology and approaches in terms of the problems that they can address. And so I'm going to focus my presentation on 3 what I view large problems that the IPY5 could potentially focus on. The first one is permafrost thaw, and specifically for me now thinking about abrupt permafrost thaw or thermokarst. Second one is wildfire, impacts society and climate in tons of ways, and the carbon budget of the Arctic, which has been brought up previously. And I think for each of these, there are big questions we could think about addressing. So for instance, with permafrost thaw and abrupt thaw, can we actually map and understand the impacts on carbon? For wildfire, there are data needs, but what should we actually do in terms of managing these wildfires? And then first, it came to my ear through Chip Miller, but it's also been brought up today. Could we actually close the carbon budget of the Arctic? Next slide, please. So starting with permafrost thaw, I think largely the motivation should be known here, but abrupt permafrost thaw and permafrost thaw in general impacts the land, people, infrastructure, can have a major impact on carbon cycling. And we still have quite a limited understanding of the distribution of abrupt thaw, changes over time, and the effects on carbon and what that's going to do in the future. So first, thinking about mapping abrupt thaw, there are big needs there. We don't really have circumpolar maps of most of these abrupt thaw features. There's been a lot of development recently, but a lot to be done. Given the size of these features, so when we're talking about satellite imagery, it really needs to be high resolution. Maxar and Planet have been brought up. They're commonly used sources, but there are major challenges with using them. So that includes both data access, because these are not free, as well as data storage and computing and processing. Now, if those challenges can be overcome, there has been a real rapid advancement and will continue, I think, in terms of AI and deep learning tools to make use of these satellite data. And we've seen great utility in products like the Arctic DEM. And because the data volume we're growing, time series analyses are becoming more and more important in this realm. And I think there's a really great potential from combining these data sources with things like repeat LiDAR. The EDGE mission was mentioned. That would be amazing. Interferometric SAR to get at surface deformation after ground ice melts. And then we also just need more training databases, validated features on the ground of where abrupt thaw is happening. In terms of understanding the impacts on carbon cycling, honestly, we just need a lot more field measurements, both in terms of carbon transport and labelity, in terms of the fluxes of CO2 and methane to the atmosphere. We need this in different abrupt thaw features and in different environments over time. And that's where models come in. So I think Charlie Kova is going to talk about this. There's been some development, but models are frankly behind on this subject. Scale mismatch is a major challenge, particularly if we're talking about global models, global land surface models. I think there are solutions. Our team at Permafrost Pathways has been working this, and really smart people like Charlie have been laying the groundwork to deal with this in large scale models. I would say one major limitation, to be honest, is that it's really hard to get dedicated funding for this type of model development. So I view that as a big need. Next slide, please. The next topic, I'm going to talk about wildfire. So wildfire in Arctic and boreal environments are intensifying because of climate change. They have all kinds of impacts on the ecosystems, on carbon, on smoke and human health, on indigenous cultural values, and more. There's limited quantification of many of these impacts, and like I said, also understanding of how to better manage wildfires. In terms of the carbon side, we have a pretty decent understanding, at least in parts of Arctic boreal North America. Siberia remains a large gap. But I also think a big gap is thinking about the impacts of wildfire on permafrost. And for this, we certainly need more field observations, similar to what I just described for abrupt thaw. So for some examples, ground penetrating radar can really help us understand how fire is impacting subsurface properties. Ecovariance towers are needed to understand the net greenhouse gas impacts of these wildfires. And satellites can certainly help tremendously, especially for telling us where and when wildfire is leading to these permafrost thaw features. So the need for high resolution multispectral, repeat LiDAR, and SAR can help us understand how fire is impacting thermocars. And finally, this is also another area where we really need development of process models. The vast majority of global scale models that include fire don't combust organic soils. I'm definitely not an expert on smoke or health, but I wanted to mention it because of how important it is. I think some emerging approaches and biggest needs relate to better emissions and smoke transport modeling, but also the really tricky business of linking that to health outcomes and developing better forecast tools for planning and community response. And then finally, fire management interventions. I realize this is a topic that differs from the traditional IPY focus, but I think it's really needed. We have to learn to manage fires better, which includes learning to live with fire, but also having more fire resilient landscapes and communities and how to intervene to limit the most damaging impacts of fires. It's an area where there's been some really exciting technology developments happening now, including better detection capabilities like the incoming FireSat constellation, unmanned suppression aircraft, and actually flying planes into thunderstorms and suppressing lightning. Some of the big needs, in my view, center around new operational tools and understanding how we sort of, what's the optimal mix of things like initial attack, pre-fire fuels treatments, prescribed fire, and really, really importantly, revitalizing cultural burning. Next slide, please. And finally, carbon cycling. So yeah, I mean, estimates are kind of converging, but there's still a large spread in the estimates of the current carbon balance of the Arctic. And of course, there's potential for large future emissions. So next slide, please. One key approach that's not going to go away, and I think is only going to increase in terms of importance and use, is the network of eddy covariance towers that monitors the exchange of CO2 and methane ecosystems as they warm. It's something that our team at Permafrost Pathways has been working on, people like in Ted Shore's group. Really hoping the momentum we're building can be sustained into the future, into IPY and beyond. We still have big data gaps, for example, in Siberia or in different post-disturbance ecosystems. We also need to sort of continue working on sort of the efficiency of data processing and data sharing and visualization to make best use of these data. Next slide, please. It's an area, of course, where we also need model development. I talked about some of the needs previously, but some of the other big needs in general, I would say, with models focusing on high latitude and permafrost environments, vertically resolved soil carbon pools to represent permafrost carbon, terrestrial aquatic linkages, improved snow physics, and dynamic vegetation, to name a few. Next slide, please. This isn't exactly my area of expertise, but I'm really excited, I would say, about the future possibilities for satellite-based column measurements of CO2 and methane. These, of course, exist today, but there are still some big sort of gaps and needs at high latitudes that could be addressed.
Brendan, can we just go ahead and wrap up on this one?
Okay, yeah. For example, upcoming missions that have highly elliptical orbits to focus on northern latitudes, or using LiDAR sensors that can bypass some of the big limitations due to darkness. Next slide. I'll just say, I think finally we're just sort of like just touching the surface of what we can do by coupling bottom up and top down approaches. I think there's a large potential there to reduce uncertainties. And then maybe just go one more. Finally, next slide, please. Sorry. I just want to stress that, really all of this work takes place across lands that Indigenous communities have called home for thousands of years. Indigenous peoples have deep, deep connections and have stewarded these lands successfully for millennia. I really believe the Western scientific community has a lot to learn, and with IPY, I think we have a real opportunity to do things better, to truly co-develop research with Indigenous knowledge holders, to center their values, and to make sure our science is serving their needs. And I'll stop there. Thank you very much.
Thanks. Okay, we'll pass it over to Esme.
Hi everyone, I'm Esme van Wyk. I'm from CSIRO in Hobart, Australia. I'm a physical oceanographer working primarily with deep Argo and under ice Argo floats around the Southern Ocean. So I thought I'd talk to you from a more Southern Ocean perspective today. And I thought before we look forward, it would be worth having a quick look back to see where we're at the last IPY. And so taking the Argo profiling float array as the example here, we can see in the panel on the left there, all of the profiles collected between the start of the program in the early 2000s to the last IPY in 2007, 2008. And you can see there's some coverage there, but the seasonal ice zone is really not very well sampled. And that was because the floats had low survivability in the sea ice zone. And so German colleagues at RV developed a temperature-based ice sensing algorithm, which enabled floats to use a pre-programmed temperature threshold as a proxy to determine the presence of ice above the float, and then decide to abort the ascent, store the data, and then move out of harm's way. And so that advance, in addition with being able to store all of the winter data and then telemeter that back in spring, plus the advent of faster satellite communications, really helped floats survive in the seasonal ice zone. And so if we fast forward now to 2025, where we are today, you can see we've really made great progress in filling in the seasonal ice zone to the point where we now have year-round subsurface measurements there. But there are still significant gaps that remain. Parts of the Ross Gyre and the Weddell Gyre and parts of East Antarctica The deep ocean remains undersampled, and Deep Argo is aiming to fill that niche. That's currently transitioning from these regional pilot arrays to a more global implementation, but that will require significant investment. SOCOM and Go BGC and other BGC profiling float efforts have really made a great contribution to expanding the suite of measurements beyond physical measurements, and been very successful. So I think, you know, the biggest remaining gap that we can see there is really the continental shelf around Antarctica, and we've seen profiling float deployments there. There's been about 100 so far, and you know, I'd really like to see that scale up to become a circumpolar array. And there are discussions within the Argo steering team happening at the moment as to whether that would be something that's part of Core Argo expanding to the poles, or whether that would sit outside of the Core Argo program. Next slide, please. So if we move a little closer to Antarctica and consider what an observing system might look like in front of, say, one of the key Antarctic ice shelves. We've heard many of the panels today talk about the vulnerability of the Antarctic ice sheet and needing these multidisciplinary observing systems to really get a handle on the processes that are happening there and to increase our measurements. And so this schematic here on the left is an old one, but it shows you the established observing technologies that we're all familiar with, such as ships, floats, gliders, moorings. And I didn't have time to update this schematic, but it's worth talking through the newer capabilities that we have and what we might be able to use in IPY5. And so, you know, we're now seeing longer duration missions for gliders and AUVs, extending from months to years, going from hundreds to 1,000 kilometers. You know, AUVs, gliders, and floats are now measuring beneath ice shelves. We've seen a big expansion of BGC and biological sensors, and they're being fitted onto many of these autonomous observing platforms, so we can now go beyond the physics. We've seen developments in uncrewed surface vehicles that can now carry small payloads. We've got development with long-range unmanned drones that can carry, for example, air deployable floats and drop them in the front of ice shelves in remote regions that we can't otherwise access. And then, of course, the work of Brittany and her team developing IceFin that can be deployed through an instrumented borehole and start making these measurements towards the grounding zones of ice shelves. So we've come a long way, and I think it's now IPY is a good opportunity to move beyond these single discipline, short duration process type experiments to a multi-platform, multidisciplinary observing system for key ice shelves around the Antarctic and also in the Arctic. And if we look at the plot there on the right, this is from a paper by Craig Lee and colleagues, which show what an Arctic autonomous observing system might look like. You know, and we've made a lot of progress. I remember talking about this with Craig 10 or 15 years ago, and you know, many of these elements of the array were at the conceptual stage, and now it's a reality. And so they've now demonstrated these basin scale long-range geolocation of floats and gliders, and then network for communication and data telemetry. And so these instruments can communicate with each other underwater and send the data back via the surface components of the array. And there's a whole lot of new emerging observing equipment like the warm buoys that you see there that make bio-optical measurements at the ocean ice interface. There's dynamic ocean topography buoys that measure sea surface height and precipitable water vapor. And so we really need to think about, you know, can we use IPY as a springboard to really develop the national, international collaborations that we need to get these observing systems in place. Next slide, please. And so just thinking about some of the next steps, many of the sessions here have raised the need to develop very cost-effective, long-lived autonomous platforms and sensors. You know, the more cost-effective they are, the more we can do with less resources. You know, if we can increase our battery power, reduce our power consumption, improve lifetimes, then we can really maximize the use of our autonomous instruments. Another thing that was raised was, are there some easy wins? So can we improve our opportunistic sampling? Can we start instrumenting some of the tourist and fishing, maybe some merchant vessels for underway measurements? We're already using tourist and fishing vessels to deploy instruments from remote regions. Can we get some easy wins with improving bathymetry measurements? There's a sparsity of bathymetry measurements from the continental shelf around Antarctica. Can we get that information from some non-traditional vessels? And we're also starting to exploit bathymetry measurements that instrumented seals can make, deep Argo floats, and also floats profiling on the continental shelf that park on the sea bottom.
Sorry to
yield that
interrupt,
data.
Esme, if you could wrap up, that'd be great. Thank you.
No worries. Okay, so the third point there just points back to that that second slide, and so we have the tools we need, and can we? They've been used in the Beaufort Sea and in the Weddell Sea for under ice geolocation. Can we expand those networks to other key target regions? And can we improve telemetry of data collected beneath ice in near real time to aid the operational modelling community? And then a couple of points there that are not in my area, but I think are important to think about. And so we know that Southern Ocean clouds are still very poorly represented in the climate models, and they lead to large biases. We need to improve measurements and have these process studies that allow us to understand the coupling between the physics, the biogeochemistry, the atmospherics. And so then moving also to the carbon cycle. As we know, the Southern Ocean accounts for 40% of the anthropogenic CO2 stored by the ocean, and that varies on decadal timescales, and we don't fully understand what drives that variability. And so, we really need more measurements from ships, from floats, from moorings, and those really detailed process studies as well. And I might just leave it there. There's one more slide, but we can leave that up, perhaps just for a brief moment.
Awesome. Yeah, thank you. Okay, so then we'll move on to our next presenter, who's Charlie Coven.
Yeah, hi everybody, and thanks so much for this invitation to speak to you all. So I'll speak about Earth system modeling and land modeling to support IPY5. My name is Charlie Coven, the senior scientist at Lawrence Berkeley National Lab, and I'll talk about some of this work that's mostly been supported by various Department of Energy projects. Next slide. So just for sort of context, I want to start off with the Keeling curve, which of course was an outcome of the International Geophysical Year, the IPY3, right? And so that's such a pretty high bar in terms of legacies of an IPY. And then going into the future of when the IPY5 would be, is if you think about the sort of trajectories of CO2 that were imagined starting around 2015 when the last set of IPCC scenarios came out. That's the time frame in which futures in which we have mitigated things and met the sort of Paris Agreement goals, or already CO2 growth rates already starting to slow down dramatically, whereas in less mitigated scenarios it's still growing fast. So the point is, when IPY5 will be rolling around is a time of likely great change in the Arctic. And in particular, what I wanted to speak about the carbon cycle and carbon cycle feedbacks, the way that's responding to climate change is going to be, crucial and important time. And so I'll be speaking, I want to address some of the same questions that Brendan and Ted Scher have brought up earlier today. So next slide. So here's if you look at the Earth system models, and particularly the land models that are used in these IPCC assessments in order to get at these carbon cycle feedbacks. I just want to put this up here in terms of the comprehensiveness of these models, in particular the representation of some of the key processes that are relevant to polar regions. For example, permafrost carbon feedbacks, something that's missing from the vast majority of these models. So all the red boxes here is our models are missing a given process, and so the ones I've highlighted here are fire, dynamic vegetation, permafrost carbon, and the nitrogen cycle. And so you see, most of these models are are missing a lot of these key processes. And in particular, when you ask, about things like like what Brendan and what Ted were bringing up earlier about these feedbacks, between fire, changing vegetation, permafrost, you kind of need to have all of these processes operating in these models in order to get a basic representation of these feedbacks. And effectively, none of the models that we have right now have all of the relevant processes that we might consider is sort of necessary to think about this. So this is kind of like the key, problem that the land modeling community or system modeling community needs to solve. Next slide. And of course, there's work on a way to deal with some of these things. So and Brendan and Ted actually both alluded to this already. That there's work on a way to get at some of these abrupt thaw and fine scale thaw features. So for example, here's a paper by one of my colleagues at Oak Ridge National Lab, Scott Painter, who's looking at the changing hydrology of ice wedge polygons under climate change and getting the sort of subsidence that occurs in the land after the ice melts out, and showing that things like the ponded depth changes dramatically from as a result of the loss of ice, the change from low centered to high centered polygons that results from that, and then therefore the change that. So these kind of fine scale processes we're beginning to develop these models, but it's a huge challenge to then apply these at large scale in order at the scale needed to get these carbon cycle feedbacks. Next slide. There have been, again, these offline permafrost models in the IPCC report. We took an assessment of all of the offline permafrost carbon models, and it's enough to say that we expect this. These are kind of some of the biggest feedbacks that aren't currently being included in the Earth system models in terms of the carbon cycle. But we need to take this kind of approach of having separate offline permafrost models and fully coupled Earth system models and pulling these together so that we can look at the interactions between these feedbacks and have a more comprehensive representation of the Arctic system. In addition, the size of these ensembles, both from the table I showed a couple slides ago and here, these are small ensembles. These are, order 10 or so ensembles, right? There's not a lot of initial condition uncertainty here, and there's much less representation of parameter uncertainty. And we know that the Arctic in particular is highly uncertain because of the difficulties of remoteness and access that have come up a number of times. And so, parameter uncertainty in these models is hugely important as well. Next slide. And so, the land models have grown in complexity over decades. This, figure from a paper that Rosie Fisher and I wrote a few years ago sort of shows the increasing complexity of land models over time. We're now including things like vegetation demography, which is a way of representing disturbance and its legacies on the land, in models. But, and this kind of complexity is going to increase. But we need, we're going to need much of our observations to test models with these increased complexity. And we also expect that, in the next decade, there's going to be some real changes to the way the models are constructed, in particular the growth of machine learning. There are a lot of empirical parameterizations in these models that have no real theoretical justification. Things like leaf phenology, that's almost entirely empirical, and is therefore very ripe for being replaced with better, the better sort of empirical models that machine learning can apply. In addition, we need to make these models faster in order to be able to run the kinds of ensembles and explore the uncertainty needed, which is going to require replacing some of the more expensive aspects of the models with things like machine learning emulators in order to allow us to explore the uncertainty better. Next slide. Another approach that we've taken for system models is this comprehensive benchmarking against observations. So we do this kind of score charts where we look at lots of different metrics, whether it's biomass or the permafrost area, both on the land and in the ocean, in order to benchmark these carbon cycles across all the models. And with this, we can say things like, well, the CMIP6, the most recent generation of Earth system models perform better against these benchmarks than the prior generation. But we need a much more of the systematic benchmarking of these models in order to make in order to evaluate whether or not models are actually improving and how to better test them. Next slide. And just to summarize, what are the modeling needs? First and foremost, right now, particularly in this moment, we need to be protecting existing research capabilities and institutions in order to build off of into the next decade. And then, we need more comprehensive representation of the key Arctic feedbacks, permafrost, abrupt permafrost and fine-scale permafrost thaw features, interactions between disturbance such as wildfire and other disturbance types, vegetation change. These are the key processes that we expect to be strong feedbacks in the Arctic, and which aren't or are poorly represented in Earth system models right now. And we need to be able to explore the uncertainty in the models through things like large parameter ensembles in order to better understand how likely these kind of feedbacks are, what the likely strength is. Better large-scale observational constraints, things like the boundary and initial conditions. So, it's one thing to build a representation of ice-rich permafrost into an Earth system model. It's another thing to know where that ice-rich permafrost exists everywhere in the Arctic and how vulnerable it is. And that it's going to require a lot of observations to do that as well. And then these kind of integrated system behavior benchmarks, so we can benchmark these models. And I'll stop there. Thanks.
Thank you. All right, so we'll finish up here in the room. Oh, right? I believe so. Yeah, with Terry.
Thank you. Let's turn this on. Yeah. Hi, I'm Terry Wilson. I am a retired professor of earth science, but an active researcher at the Byrd Polar and Climate Research Center at Ohio State. I'm going to take I can do that.
It's turned on. Let me just turn it on.
Oh, I can just say it. Do you want me to?
There you go.
Oh, wait, then I have two things to keep track of. I'm going to take a little different tack today in what I want to discuss with you. And I want to draw on my experience from IPY4. And I was a leader of a project known as POLNet. It was an IPY4 umbrella project with different experiments going on in both the Arctic and the Antarctic. It was also an NSF-funded IPY project, and I was the lead PI with that, with many other people. And what we did was put out autonomous remote GPS and seismic instruments at remote sites. So we had lots of failures. And in 7 minutes, I can't tell you those, so I'm going to tell you about what I think are the successes. And although I'm going to use examples from this project, I think they're applicable to the development of any IPY project as you think about what might work effectively. And I want to say that I've had many collaborators and co-PIs throughout this who made this project a success, but these are my opinions and reflections on how things have gone. So this project actually is still running. So we're closing in by the time we should have pulled everything out. It'll be 20 years. So a lot of lessons learned. So how do we get there? A lot of this is pre-IPY stuff, which is where we are now, and people should be thinking about. So we built an international community who came together, decided on priority science questions and what was needed to address them. We did this through SCAR, and there was a scientific research program that brought us together, and we did this in the early 2000s. And then when it was clear that we wanted to make autonomous systems to make these measurements, we got together with NSF and NASA-funded facilities in the US, which were then called Pascal and UNAVCO, now EarthScope. And we partnered with them, got NSF Major Research Instrumentation Award to develop the power and communication systems to make this possible. So this was already underway, barely, 2006. Remember, IPY started in 2007. So it was going, but we were scrambling. So IPY happened, and this is the global POLNet here. So I have these slides for Antarctica and Greenland, pre-IPY, autonomous GPS or seismic systems during IPY. So we really threw a lot of projects that were all funded independently and nationally. We put all these experiments out for the IPY period and really made an observational step function from these systems. So what I'd like to tell you about what I think worked well are these points here about the infrastructure, data, training, and funding. So autonomous instrument systems in the terrestrial environment. I've listed 6 key components they all need: sensors, power, communications, hardiness, transportability, and ease of assembly. And of course, they all need to be, and oh, I should say that there's all this talk about new and advances in technology. We're still using the technology from IPY4 20 years later with some incremental improvements, but it's still working. So I guess that's a testament to the design. There are new sensors with lower power that we haven't had the money to integrate, but you could do. Power, as Matt Seifert said, is essential. We have batteries, essentially car batteries, that we deployed in 2007 and 2008 that are still powering our systems. However, we have 22 of them at 75 pounds each, but they work. Communications is a big one. For GPS, we can get our data back in near real time by Iridium. And so that's very powerful for science. Seismology, that's not the case. You have to physically go there, visit the site to get the data. So we really need higher bandwidth systems for data transfer. And of course, if we can do that, we reduce the logistics footprint because we don't have to go there unless it's broken. If we can communicate with it, we know whether it's functioning or not. Increased data bandwidth and lower power, or having more power on site for more experiments, makes much more science possible. So there are improvements to be made, but we're still chugging along. There's a lot of discussion already here and thinking about multi-platform sites. And the ideal scenario is always plug and play, power and communication systems. You come along with your sensor, add it to the system and collect data through that. And it leverages the investments, increases the science value. I'm a little ambivalent about how much it actually helps in saving on logistics, because for installation, you still need to get all that stuff there. But once it's there, maintenance visits become much more manageable and feasible for multiple projects. Open data, I just really want to proselytize, because we found that our data that we collected for our personal project science that we were funded for has been used for a whole range of other studies, and you heard already about the geospace use of our data. So it's really important. An example I want to point out that could be transferred to IPY is that we have cheap Iridium through the US Antarctic Program, and the Antarctic Earth Science Program at NSF has actually agreed to pay for Iridium data transfer for GPS sites, and then it goes into an open data archive that everybody has access to. So cheap investment for a lot more science. And okay, I'm going to finish with capacity. We've talked about needing the next generation, and I want to suggest an approach to you. We have, as part of our outreach, run training schools on glacial isostatic modeling. That doesn't really matter. Modeling skills were obviously part of it, but a key part for IPY is we put a lot of effort, structured activities into the participants, building peer networks, meeting mentors, and meeting other international scientists, which they could then collaborate with the future. And I would suggest that this is a pathway that we could use explicitly for IPY. And okay, I'll just mention this. There's a couple ways these have been funded, but I feel like for IPY, it would be so helpful to have multinational funding mechanisms and mechanisms that would allow different nations to pool funding. We could contract logistics, we could pay for a consortium of data transport, those kind of things. They don't exist right now. And we could consider partnerships with expeditions with private and public funding. And this is something that happened last season, collecting airborne radar data around the grounding line with a private expedition. And so here we are. Stephanie Compo made this graphic. Okay, we started, whoops, almost, I'm not really wanting that. We started last IPY making observations, discoveries, drove modeling that allowed us to then train the next generation of people. We're at sort of the culmination of that cycle. It's time to reboot it with the ideas that we're having here. And I hope I've given you some ideas of approaches that work for the last IPY that we could implement this time around. Thank you. The summary slide is for you.
Thanks. All right. So thanks, panelists, so much for kicking us off there. So what we're going to do now is kind of transition over to a panel discussion. We have a couple of questions that we've kind of set up to talk about, but I wanted to actually ask, there's a little bit of overlap in what a couple of the speakers mentioned with regards to remote sensing. So I wondered if we might transition into this kind of discussion as using that as a framework. Are there particular spectral bands, repeat frequencies, or other kind of techniques that might be overlapping between the ice sheet remote sensing that that Matt had mentioned with, for example, some of the scales of observations of margins that might be needed for permafrost thaws, for example? Maybe anyone could take it. So I was thinking repeat frequencies or spectral bands, or another observing parameter that might be common across those that would inform satellite discussions. Any panels?
I was going to let Brendan talk first, but I guess I can. I think one of the things I think about a lot is our lack of 4D, right? We need 3D through time. And that goes across all of this. And you're absolutely right. We need to constrain kind of time space scales for that. And so I think one commonality between permafrost and ice sheets is seasonality is changing, and sometimes the seasonality is changing in ways that we need obviously subseasonal measurements in both places, down to kind of at worst fortnightly-ish repeats to be able to see the impulsive events that really seem to change these systems. So I also think we've worked in our 4D sense along tracks from space so far. We do airborne LiDAR, and when you get that swath, it really is transformative in what we can do. And so I think we truly do need to take a step change into swath 4D measurements at kind of weekly, maybe a couple week timescales. At the poles, we have the convergence of ground tracks, which is really helpful. So that increases our temporal resolution quite a bit.
Brendan or Charlie, did you have any comments on what might be useful?
I was gonna say, yeah, I mean, I completely agree with that. I mean, I think, yeah, I think just stepping back, I mean, I think LiDAR is a great example, right? Madden is working on the Edge team of where, you know, the types of data collected can be extremely useful for multiple parts of the cryosphere and sort of the ecology and permafrost. So, you know, we've been able to, for example, leverage ICESat-2 to some extent, but it seems like Edge, if it were to be funded, would sort of really up the game in terms of the number of measurements and getting at that 4D. I think radar, I'm not a radar person, but radar I think also has large potential to measure things that are important in terms of, you know, sea ice and snow, but also, you know, permafrost and surface melting, and, you know, to be able to make interferometric SAR measurements that can help get at like deformation and related to permafrost processes. And so, yeah, I think that the key is sort of like to understand how to design those satellite systems so that they can be optimally useful for both, like, you know, in this example, like ice sheets and glaciers as well as terrestrial environment. And that's not always possible, but having folks on the science teams from those different disciplines where you can, because some of the biggest advancements we've had in the past have been from satellite systems that were designed for one thing. Oh my gosh, it's actually useful for this other thing, right? So I think having like an interdisciplinary science team that's helping advise in the specs of these satellites can really pay a lot of dividends.
Yeah, and I totally agree with everything that was just said. And also, I just want to add that, you know, getting the 3D or 4D, you know, ability to look at changes to vegetation structure in the Arctic as well is, you know, as we expect tree line to start to be, you know, changing in particular.
Can I just add one more thing, Brittany?
Sure, just real quick.
Sorry. And I just, the same way you said, technology doesn't replace people in the field, it supports it. And I think remote sensing is one of those things that really supports where we go, right? This is what drives where we need to get the sort of ground data that is super expensive logistically, human resource wise. And so that's why this remote sensing data is so important. It gives us a monitoring capability, but also guides exactly where we need to go. And so if we don't have that, right, we're basically throwing darts at really large regions of the world.
So moving towards some of the in situ capabilities that were mentioned. So there were a few, but I wanted to think about things that might be in common, Arctic and Antarctic, in terms of technologies and capabilities that might be fundamental to addressing some of these kind of in situ data collection from carbon to the ocean. So Matt, I know you mentioned these. We've talked relatively less about them, but if folks wanted to comment on access technologies, that might be something to highlight here. And that would also improve what Esme was talking about under ice kind of observation networks as well, and being able to communicate with mobile platforms and things. So if, perhaps Esme or Matt, if you wanted to comment on either of those.
Sure, I guess I can dive in. Yeah, so I guess, you know, looking at the example of the Arctic Autonomous Observing System that's in that paper by Craig Lee, you know, having those networked capabilities, both for comms and data telemetry and geolocation is really critical beneath ice. And so, you know, having that now demonstrated at basin scales is a wonderful advance. And, you know, if we think about the Antarctic, we've got, there's an array of moored sound sources in the Weddell Sea that have been used to track floats carrying RAFOS receivers in that particular gyre. But, and then there's been individual process studies in front of ice shelf cavities where gliders and floats have gone into the cavities, and there's been moored sound sources moored on the shelf in front to get geolocation into the back of the cavity. And so, you know, having those capabilities is a great step forward. And I'll leave off there and pass over to Matt if you have anything to add there.
Yeah, as a geomorphologist taught me about the Sadler effect once. And so I think we suffer from a variant of the Sadler effect where we don't know how episodic our processes are because we're recording it in such a poorly resolved way temporally. And I think really where autonomous measurements and particularly networked instrumentation comes in is it allows us to react to an event that we've never seen before, right? We don't need to wait around for the next one. Oh, we saw this really crazy process, right? Now we write a new proposal to go actually try and instrument it for that process. We can target a process in real time with autonomous capabilities where it senses something and then it can, you know, send out its swarm of drones or swarm of underwater vehicles or move a radar around while moving an autonomous vehicle around underneath an ice shelf. Well, the radar on the surface, ice shelf, sub-ice shelf robotics too, right? That's where the magic really, I think, will come from autonomous observational platforms in my world. But again, you need power before any of this. And so I don't know, I think about problems in a really structural framing a lot. And I think power is that sort of key structure that will enable a lot of this.
So I guess there's a question here that's actually kind of related theme that's coming up online, which is the way in which or the types of infrastructure that we choose to invest in, either platforms, so things like drones or vehicles, wheeled platforms, some of the autonomous mobile platforms, or things like Argo and other platforms those are a targeted investment by NASA or NSF or a funding agency. How do we get what kind of community consensus do we need in order to make those more prevalent or easier for the community to access and then deploy?
Well, I can comment. I think from an NSF program manager perspective, they want to see community recommendations that are reached by consensus through some mechanism, typically a workshop, and a little report that says, here's the priorities, here's the consensus on the compelling science and the measurements that are needed, and these are most important. That's something that they, as managers, can lobby up the line in their systems to argue for funding in that direction relative to the other competing interests.
I guess I could comment on that as well. I think it's something we've thought about a lot in the Argo community. And so I see on Slido that Lynn made the point that, that transformation of coverage in the Southern Ocean for BGC floats was driven by NSF funding. And that's a really important point, particularly in these uncertain times now. And so the US currently funds half the global Argo array. And so if that was to change, then our array would look very different. And so, we've also talked a lot about in the community, many of the programs are funded through their own national programs, and it's research funding rather than operational funding. And so we've talked a lot about building collaborations with the operational community to really emphasize how critical these broad-scale ocean observations are to underpinning operational modelling and forecasting. There's a One Argo paper that's due to come out soon that really that does that nicely. It talks to all of the different stakeholders and engages the operational community. So I think that's one way in which we can make the case that we need to move from a research funding base to an operational funding base for some of these autonomous observing systems.
Yeah, so that was a great point. And I wanted to point out that there's been several questions about basically investments in those types of architecture, making them longer term, talking about timescales. Obviously, as we're talking about remote sensing aspects, Polar Geospatial Center, we all know what's happening with that. So these are valuable kind of decisions that the community kind of needs to support, but then funding agency put in place. So this kind of shift in how we do things. Yeah, Matt, you had a question or?
Yeah, I was just going to make a comment while I have a platform. Terry went through a lot of successes, and I wanted to highlight a failure, which is as Brittany also knows, for about 10 years now, 12 years, we've said the community has put forward white papers through a facility that has, put hot water drilling to access the bed as one of these basic high priority requirements that we need to develop in the US, and it still doesn't exist. And so I've been frustrated by how when there's community buy-in and things aren't happening, the community buy-in is not leading to investment. It doesn't seem like we have a lot of mechanisms to handle that, at least in the US. And so I'm to be honest, pretty burned out on this sort of work, right? Because we've been working on it for so long and we haven't gotten anywhere. And so I think we need to have a really frank, deep discussion with the NSF about how we run facilities at through the US and how we take community buy-in and use it to leverage and accelerate success in science.
Yeah, this is kind of related to as well another point that I wanted to bring up, and I think is thematically linked to a couple of questions here, which is, so I think your point about access drills is a good one. They exist. But that's an existing technology. It's not even that far out of, it's developed and exists in other countries, and then we've just kind of chosen to not have. But there's other examples, which are there's lots of technologies that people talk about bringing on. But the question I think also is, who decides which ones are technically feasible and important? Who's going to build those things? We've seen a lot of let's hand it over to a company and hope nebulous company, with potentially no profit model for how to keep that technology going is going to just supply us with that technology. And so these kind of, what you're describing there is kind of a development or a long-term timescale or decision process for how to get those technologies into a place where the community can use it at large. So, I'd hope that workshops like this are helpful for that, but I agree, perhaps a better version of a decadal survey or something like that could be something that might help us with decision making. Are there other comments from the panelists on how we might, as a community, advocate for those kinds of investments that need to be made in these technologies and platforms and then data systems?
I don't have a ton to add, but just would say it's the kind of subject where international coordination I think would also be really helpful, and thinking about existing bodies that can help with that. For example, in the Arctic, thinking about an organization like the Arctic Council, right, that tries to work across the 8 governing nations in the Arctic and try to come to consensus on issues and puts out reports, for example, on protocols and methods. And so, yeah, thinking about it both domestically, NSF, but also internationally, and if we can get consensus internationally, it's probably stronger.
Yeah, so we're unfortunately, because we were running behind, we might need to stop there and then have our World Cafe breakouts. But yeah, thank you. I also thought that's the kind of thing that also might help with computer infrastructure, right? With these large scale models that require more and more resources. It's the same kind of decision, like where is the resource going to be housed, and how long do we maintain it, and how do we make those decisions as a community? So thanks very much to the panelists, and we'll capture these questions that we weren't able to get to online. Perhaps they'll drive future discussion. And at this point in time, we're going to break out into our kind of interactive sessions. So I'll hand that over to Morgan.
Awesome, thank you. So I think we're going to do a very similar thing to what we did last time. We have 4 new or different moderators for these sessions, and it'll be 10 minutes again. So you have 10 minutes for discussion, then we'll rotate moderators the same way we did last time. And then we will come back into plenary to have a report out. So what I would like to do though is you can kind of stay in your same groups. Let's send the group that was in here with no windows before. You guys can go outside this time. The group that was outside, you're going to stay in here. The group that was in the cafeteria, you guys can go to the conference room. And the conference room group, you guys can go to the cafeteria.
Hey, everyone. We're going to get started now with the readouts from the World Cafe. So we're going to have 8 moderators come up to give us a brief summary of what they discussed as they rotated around, and be about 3 minutes, if you can try to keep it to 3 minutes if possible. So we'll start with Kirsty Tinto.
Thank you. Okay, I was attending to question number 1, which was what new or emerging technologies or capabilities could be utilized to address the research areas discussed in this session. And we had a lot of different ideas. I'll miss a lot of them, but I'll capture some of the key points from each group. So there was conversation about that we need improved battery technology, we need improved data telemetry, we need to have autonomous instrumentation that's able to run for a long time, ideally through winter. The idea came up from here to build on what was said in the earlier session about instrument kits, where you get economies of scale of acquisition. You can have communities come together to develop protocols for using particular instrument kits. In this group, they were talking about DAS technology, so fiber optics, and the sensing that they can do and the information they can convey. We also wanted to track through the whole data lifecycle. So there'd be agreed protocols for using this information. There's emerging software that can be used to analyze data that come out. That came up talking about imagery. And then we need to have communities coalesce around metadata and archiving structures. That took in a couple of groups worth. We want deep access hot water drills. We should be able to do that. And helicopters are essential. It's not an emerging technology, but it's essential to be able to do the work that we need to do. We want to have smaller, higher powered instrumentation from SEALs. That all came together. There was a call for a seafloor geodesy and undersea GPS, that we could have a real international collaboration to instrument under ice shelves and get a tremendous amount of information conveyed through those systems. There was also a lot of thought of what we need for atmospheric measurements, that we need to be able to really well measure stratified environments and to track along with air masses. So what kind of vehicles would be used for sensors was an important part of that. We even got into citizen science and how we're going to engage human energy as an emerging technology, and ways that some of these technologies can be used and shared with people who are living in polar environments, and that could be a really great pathway for developing new technologies, having them tested somewhere so that they're really fit for use, and then deploy out into the uninhabited areas of the Central Arctic Basin and Antarctica. I was only given 3 minutes. There were many more thoughts. I'll write them down.
Thank you for a wonderful summary. Great thoughts there. So we're going to move on to Dave Sutherland. Please go ahead.
Thanks. Yeah, I'll follow on with Kirsty since we had the same question, but online. A lot of what we talked about, I think, was a theme around how models and observations actually interface. We ended up talking a lot about AI and how we need to get better at understanding the assumptions and training data that go into AI technologies, and also test the new AI models coming out. So that was a lot of our conversation. Along the same lines, sort of new model development, right? There's some cases where the models that we currently have can't reproduce observations and processes that we know exist. On the flip side, there's certainly some models that are simulating processes that we don't have enough observations of. So using those sort of together to iterate on would be good. Maybe one way to do that is to think about a digital twin. There was talk of this, even though there wasn't much understanding in our group, I'd say, of what a digital twin is. But the EU is building a digital twin of the world's oceans, and it might be something to consider to have that capability before IPY. We talked about the emerging, low-cost sensors that people use for measuring CO2, methane, and other gases, and getting those, into the hands of researchers that are going out in the field, so they don't feel like they're limited by the use of really pricey, expensive instruments. So, just expanding the spatial scale. On the ocean side, there was a lot of talk about these amazing one-off, instruments that we do have, especially underwater, unmanned vehicles, things like Nereid or IceFin or AutoSub, and how do we actually expand the use of those so that they're not, used so infrequently or in one location for a few years. So how do we use those capabilities more? Drone-based mapping, right? Drones are just continually getting more and more capable. So drone-based mapping of land, soils, vegetation. Let's see, what else? There was a mention of NASA's new investment in a 777 for some, particularly for doing flights over Antarctica, I think. And then also, how can we utilize more long-range UAVs to do, for instance, ice radar of the ice sheets to get better bedrock topography resolution. So those are some capabilities that we have that I think could be used. There's this tension in this room for this question number one to always want to talk about what we want and not the actual technologies that we have and use. So I think we delved into the sort of wishes more than the actual, new technologies that we actually do have. So I'll end there.
Great. Thank you very much. Let's move on to Lindsay Goodwin and also move on to the second question. So go ahead, Lindsay.
Cool. Folks in the room can hear me?
Yep, we can hear you.
Cool. For some reason, I can't see you all. I just see a picture of Dave, but I hope everyone can see and hear me. Cool. So the question that we discussed are there any novel tools or approaches to consider, including from other disciplines, applications, not typically used in polar research? And there was a lot of cool comments. I'm not going to quite give it in chronological order, but I'll try and capture everything as much as possible. There was an interesting discussion of the technologies that we would want to see in Arctic, like in the polar regions, including like thermal probes and possibly like utilizing sensors on barges that bring supplies into certain regions. But there was also a really interesting point about like we need to be mindful about what kind of technologies we want to use during IPY. We need to basically like, given the timeline, we should be taking like proven technologies and making more feasible rather than trying to think of something that's wildly risky and might not work at all. So a good example is like in fiber optics. We understand how the fiber optics works. Let's not get too over the top, risky with given our timeline. It was also mentioned that IPY is a great time to start a long-term study, and there is actually like a little bit of a history of like starting new like incredible sciences at the beginning of IPY. So like we shouldn't necessarily use risky technology, but it'd be really cool to like think about like what studies would we like to start. One study that was brought up is like a broader study of like how does old carbon get into like new carbon cycles. So basically better monitoring of like carbon cycles. Someone in the Padlet talked about like proper validation of assumptions and models and how a lot of like the research that we're relying on is like has not been properly validated, especially the measurements they hit on. But then there was like some interesting like people related discussions that came up. First of all, or not first of all, but like someone mentioned that there was like a lack of studies related to disease like bird flu and genomics. And then a really interesting point was brought up is that like we have disease in the regional seabirds and have been told by NOAA, I'm reading this as a quote, to expect it in our sea mammals this summer. We, and I believe this was Gay, Gay Sheffield, we are living here with little to no surveillance and monitoring of the marine resources essential to coastal communities, nutritional, cultural, and economic well-being. So in other words, like there's a huge gap between like the diseases that we should be monitoring and like kind of like what is actually being done right now. So improvement in those regions would be excellent. But there was also interesting discussions related to like communication with regional hubs that like kind of piggybacked and related to that. And like even just cold calling, reaching out to like these regional hubs in like Alaska would be perfectly awesome. This would be beneficial for like teaching folks in the area how to use instruments and to get more involved in science. And we can get the experiences of people who like have been living in these environments and the anecdotal evidence to understand these sciences more. And one cool point that was brought up is that like we could be like utilizing like the like observations of like long distance swimmers because they would like have an experience that like a lot of us would not have and could really bring some interesting perspectives to the table.
Thanks, Lindsay. Can you wrap up?
Sure. The last thing I'll say is that there wasn't enough discussion about communication and looking for community and public partners. And like, it seems like more people would like that. And like, if it was possible to have an IPY science coordination office, that would be ideal. But that's all the points I want to make. Thank you.
Thank you very much for a great summary. Can we go to Scott? Scott Kovitz. Sorry, I should say your last name too.
Okay, we get this right side up. Okay, yeah. We had some good discussions, zipping around amongst the groups, and as you just heard, we talked about omics as well as sort of tracers that could be could be used in different systems. And then, let's see. We talked about, as Matthew Siegfried spoke to, as part of his presentations, we talked about drones, swarms of drones, undersea ice operations, and drones, or those sort of autonomous vehicles that can communicate with one another and coordinate with one another. We talked just a bit about new satellite technologies, which some of us here know a good bit about, EDGE and STV, surface topography, as well as airborne technology demonstrations that could be done. We talked about data systems, like cloud-based systems with ability to sort of mess with the data real time and share it with others real time. There's a currently existing system that a number of people are collaborating on doing sort of global biomass models that may be applicable to polar research applications, something called MAP, M-A-A-P. We also talked about AI in a couple different contexts and how that could help in various ways. Something about creative logistics to ensure supply chains in terms of not just people, but supplies for remote locations where people were working out of, and creative ways to get beyond that. A little bit about how to deal with the fact that we can no longer access this tremendously large terrestrial land area in northern Eurasia, Russia, that's critically important for our understanding of the system. Creative use of social media. Also talked about virtual reality and some of the potential to use that in the field, at least to bring students into like the virtual environment and experience what it looks like. And that could also actually apply to decision makers as well, to help them get a sense for an understanding of what we're doing in the field and what we're measuring and so on. So I might leave it at that. There's a whole list of other things here. Oh, one interesting thing that also came up is just getting access to, what was previously classified data. We've done this a lot in the terrestrial realm in terms of vegetation change, but there's probably an enormous amount of data, bathymetry and beneath the sea or beneath the ice measurements that could be leveraged.
Thank you very much, Scott. So we're going to move on to the third question now with Oscar Schofield. Sorry.
All right. We were the international group facilitating cooperation. Are we going to be international? Yes. And it came up in one of the groups that it's a unique time in the US to be talking about these international partnerships. But really, as a community, we should be facilitating those partnerships, especially for young scientists at this particular time, since they will be leading the IPY. And that needs to be a mandate we do. And to facilitate that, we need to make sure we clarify how you form those partnerships in a formal way. Lead agency agreements can be complex, they can be landmines, and we should help facilitate those. And also expand out to external people. Schmidt has a training group, other groups like Woods Hole has leadership training for young scientists. So we should continue to facilitate those and expand it maybe to technologies that would be appropriate. To also expand collaboration, development of standardized kits, plans, we've heard about it, potentially libraries, for checking out. But the key thing is also having a calendar of opportunities and having the calendar be far enough in the future so a scientist or a local community has time to apply to actually get to use the kit. It's a sign when you become a senior scientist when it's no problem. I got 24 hours. I'll crank out a grant. We don't want to train people the wrong way. Also to develop community efforts through common portals. The MAP program came up again. I think that's a really unique, cool sounding program to facilitate algorithm development. And develop common portals with data visualization tools, have DOIs. So if someone contributes, you have something you can put in to essentially your promotion packet to go for it. So how are we going to do it? There were two models that fed off each other. Community grassroots using societies we have, SCAR, SEUS, IESCA, the Arctic Assembly. Those facilitate working groups. They provide little pots of money. And you sort of see what ideas rise to the top and have legs. It may not be that it's a better idea. It's an idea that refuses to die sometimes because of a champion. And that's actually what you're going to need to get over the hump. Engage operators, whether it's ships of opportunity or CONMAP in terms of those that actually regulate it. And you combine that then with the top-down agency control. NASA above was an example where you have international groups developing steering teams that provide a big vision for technology development. And hopefully the societies feed into that steering team of what the priorities are. Two final things. Facilitate sharing infrastructure in a new way. And that could include if we put drones, AUVs, gliders, all these things in the water, why can't we fly between our stations, rebattery and fly them back and fill ship gaps that we all have, you know, and that would be a whole new framework for it. And finally, it came up, joint undergraduate, graduate teaching symposium actually is classrooms where the students interact together on a single problem.
Thank you very much. Let's move on to Melissa Shapiro for the online breakout.
Thanks so much. So I was with Breakout 3, and we addressed two questions. The first was, what is the role of international collaboration in fostering the development and use of new capabilities and approaches? And one of the themes we discussed was how programmatic coordination can kind of help close gaps for kind of more robust knowledge sharing. And an example of this was specifically highlighting a workshop around ASSW that focused on providing a more comprehensive picture of vegetation around the circumpolar north. We also thought the role of international collaboration could help to facilitate technical funding and resource sharing benefits. Examples of this were international sharing of specialized equipment like icebreakers with helicopter capabilities and collaborative development of sensor networks and drilling capacities. Furthermore, international collaboration can help address existing inequities and exclusions that exist in science. An example that was highlighted is that research is conducted and published primarily in the English language, and that there's also an opportunity to build more equitable practices into collaboration frameworks. We also recognize that there's a lot of foundational work that can start now. So relationship building needs and training takes time and really should begin well before IPY5 so that IPY5 can mark the beginning of something significant, and we can really see some signs of progress by that point. And this includes some conversations with international funders about co-funding possibilities, as well as some cross-border mechanisms to support researchers and stakeholders. All of that takes time. And lastly, we did sort of note the connection to broader international frameworks like those of the UN and International Science Council, and acknowledge that historical instruments, entities, and processes like the World Data System have originated from past instances of international coordination, but may not have been carried through the last International Polar Year. The second question that we addressed is what type of experts or groups would need to be involved in fostering these types of international collaborative relationships. First, we did acknowledge that there's different collaborative dynamics between the poles. So for the Arctic, it's really important to center Indigenous communities and values. Indigenous peoples really should be at the center of collaboration, making science relevant and aligned with their values, and recognizing that a lot of the polar research takes place on Indigenous lands. But circumpolar north and south, we recognize the importance of robust nation-to-nation cooperation. We also talked about just existing structures like the Scientific Committee on Antarctic Research, community building specialists, science communication and education experts, existing international organizations, those with specialized scientific expertise, and also cross-disciplinary collaborative facilitators. And
Can you wrap up
some
soon?
examples.
Sorry.
Okay, that's fine. I'll be done. Thank you so much.
Thank you very much. Appreciate it. We're going to move on to our last question with the online breakout. Fiamma Stranio, sorry, apologize if I mispronounced your name.
That was perfect. Great. I get to be the last one holding everybody up. Okay. Thanks to all who participated in our breakout. I'm going to try and be brief. Our question was, are there any technologies or approaches where researchers may be able to help inform development so as to support polar research in IPY5? And so we talked about a number of technologies. Some of it has to do with increasing use or optimizing use of existing technologies, but also deployment of new ones, including, for example, underwater cables that can be instrumented with additional sensors, as well as used for fast data transfer and communication. We had a number of oceanographers in our group, so we talked about higher density acoustic tracking for under ice and under ice shelves observing in the Arctic and Antarctic. There was a lot of discussion about new remote sensing missions that are focused on polar observing and the development of systems to track marine and terrestrial polar ecosystem through biologging and all the way to environmental genomics platforms. Another theme was addressing undersampled regions. We identified the continental shelf and coastal polar regions as regions where we still have scarcity of data. And we talked about preserving access to some of these regions through icebreakers or the establishment of new drilling capabilities. We did talk a lot about preserving existing capabilities. This should not come as a surprise, given that we are seeing some disappearance of data centers or reduced opportunities for workforce in the US. So this is really important, including supporting long-term capabilities. And finally, in terms of approaches, we talked about integrating multiple discipline in any observing system and in system description. So the need to really incorporate physics, chemistry, biology, as well as stakeholders in addressing polar questions. We discussed real-time data capabilities as a means of obtaining forecast of some quantities that are societally relevant. And again, a focus on developing methods to address community-driven questions. And I'm going to end here.
Thank you very much. Appreciate it. We're going to move on to our last summary from Hyomin Kim, also for this question.
Okay, so the question about how do we share information about technology and approaches. So we talked about the issues, basically, how do we bring all this community together, especially like, scientists who don't really necessarily know about technology, engineers who are not actively engaged in science itself. So how do we bring all this, different ideas together? How do we share these ideas together? So we talked about, the technology already exists, but, deployment ready in the harsh environment is very difficult. So, I think it's more frequent conversation is needed. So one thing that we talked about was as a common platform, such as workshop or school, where, people can sit down together and share ideas. One example is Polar Technology Workshop that I wasn't involved in before, that National Academy of Science actually organized before. But that's not really happening on a regular basis. So maybe we talked about need for having more frequent workshop kind of event where people can sit down together. We also talked about directed proposal call, so that proposal that can bring, experimentalists and the modelists together so that they can work together to promote this kind of, sharing ideas. We talked about, how difficult it is to conduct like short-term project given like very short-term budget to make this kind of project more sustainable. And then we talked about facility development. Community runs infrastructure, but some particular community runs infrastructure, but sometimes they need to listen to other community, their need, so that community the runs the facility operators, and then logistics contractor, for example, USAP, should sit down together to have better, to more efficient and synergistic conversation. Then also we talked about common platform for data distribution, modeling, development, so that for such as like machine learning or AI technology that computer science community can contribute to, and then how do we work together? Can you have school or workshop kind of platform? And then lastly we talked about how more frequent and clear conversation across the board is necessary. Experimentalist, software developer, model person, and logistics company like such as USAP should sit down together to have more in-depth conversation to how to move forward things. So.
Thank you very much, Xiaomin. And I just want to thank all of the moderators and also all the participants for a wonderful conversation. I think there's clearly, apologies for cutting some people off. There was just too much to talk about in all of these sessions and also summarizing them. So there'll be plenty of more chances to provide feedback tomorrow and in future meetings. And with that, I'll just say that tomorrow, reconvene here at 10 a.m. for another round of fun discussions. And also for those who are here in person, we can continue the conversation in a social hour at Clyde's of Chevy Chase, 5441 Wisconsin Avenue. So head over there if you're interested. And with that, I'll just say again, thank you so much to all of the participants, all the moderators, and everyone who participated today. It was really wonderful. Thank you.